From the trunk of a towering elder to a struggling sapling in the shadows, a silent gift flows. Life. Think of that elder not merely as a tree, but as a guardian, a keeper of ancient wisdom, and a nurturing force watching over the entire forest. In a world that often feels divided, rushed, and disconnected, it's comforting to know that somewhere, in the quiet, nature still remembers how to care for its own. Step into the cool hush of a forest, and you might assume the only communication taking place is the rustling of leaves or the chirp of a squirrel in a distant branch. After all, trees don't talk, or do they? Well, not in the way we do. They don't use sound waves or vocal cords. But as science is revealing, trees do communicate. They converse in ways that are subtle, clever, and remarkably effective. We've already explored their underground networks, but tonight we journey above the soil, where trees have another, more surprising method of talking. Yes, trees speak on the breeze. When a caterpillar or beetle begins munching on a tree's leaves, the tree doesn't just accept its fate. Instead, it sends out chemical distress signals, airborne messages that travel through the forest. These volatile organic compounds, or VOCs, can drift across dozens of meters, warning neighboring trees of the danger. Upon receiving this signal, nearby trees prepare for attack. They start producing defensive chemicals, compounds that make their leaves taste bad or even toxic to the invaders. It's a form of preemptive defense, a chemical warning system triggered by one tree but protecting many. Incredible, right? But it gets better. These chemical messages are not random, they're tailored. A tree being attacked by a specific insect will release a particular blend of VOCs designed to counter that insect's biology. It's a bit like sending an emergency broadcast with details specific to the threat. Attention, caterpillar attack. Deploy bitter-tasting compounds. Some trees go even further. They call for help. That's right, they summon reinforcements. The VOCs released can attract the natural enemies of the attacking insect. For example, if aphids are feasting on a tree, the tree might release a scent that attracts ladybugs, the aphids' predators. It's not just defense, it's strategy. This form of communication works across species too. Plants of entirely different kinds can respond to one another's VOCs. This interspecies eavesdropping turns forests into responsive, adaptive ecosystems where every plant is listening and talking in its own way. What's even more fascinating is that these signals are dynamic. A tree doesn't always respond the same way. Its response depends on the context, how much damage it's taken, how many neighbors are nearby, the time of year, and even previous experiences. Yes, trees have something akin to memory. If a tree has survived an insect attack before, it may react faster or stronger the next time it encounters the same threat. This isn't memory as we know it, but it's a biochemical learning process that improves the tree's chances of survival. A form of biological recall. Let's pause here. Take a deep breath. The air you just inhaled may contain more than oxygen and the scent of pine. It may carry messages, stories of attack, resistance, and survival, drifting invisibly between branches. The forest isn't just growing, it's thinking. Slowly, silently, strategically. And humans are only just beginning to understand this language. Scientists are now studying the specific compounds trees emit, how other plants interpret them, and what it means for agriculture, forestry, and climate science. At infinity beyond, we marvel at the stars, but the intelligence found in forests is no less cosmic. Here on Earth, trees offer a form of slow wisdom, a dialogue that spans days instead of minutes, but one that is no less real. Perhaps we were too busy to notice before. These discoveries don't just change how we view trees, they change how we view life. Intelligence may not require a brain. Communication doesn't need words, and defense doesn't need violence. The forest's language is cooperation and response, spoken through chemistry and connection. And what about city trees? Are they part of this network too? The answer is partly. Urban trees can still send chemical signals, but their connections are often disrupted. Limited space, concrete barriers, and fragmented root systems mean that city trees are often cut off from the forest internet. It's like being online with poor reception. They're still talking, but the network is weaker. That's why urban reforestation and green corridors are so important. They don't just bring beauty or shade, they restore relationships. They reconnect living beings in a web of support that benefits everything from soil microbes to human health. So what can we take from all this? We've spent centuries seeing trees as static, silent, and solitary. But the truth is far more vibrant. Trees are dynamic participants in a living, breathing, responsive ecosystem. They share, they defend, they remember, and above all, they communicate. So the next time you hear the wind rustling through leaves, ask yourself, what might the trees be saying? Listen closer. The forest is never truly silent. If trees are the voices of the forest, then fungi are its telephone lines, quiet, hidden, yet absolutely indispensable. These humble organisms, often overlooked and underestimated, lie at the very heart of everything that makes forests function. The towering cathedral of trees, swaying in the wind, may capture our eyes and our imagination, but without fungi, that cathedral would never stand. Or more precisely, it would never have existed to begin with. Let's return to our unsung heroes, the mycorrhizal fungi. These fascinating organisms belong to a vast and diverse group of soil-dwelling fungi. Their gift? Forming deeply intimate partnerships with the roots of plants, a connection so vital that nearly 90% of all land plants rely on it. It's a relationship built on trade and trust, refined over hundreds of millions of years. The deal is simple. Fungi receive sugars, the carbohydrates produced by trees through photosynthesis. In return, they extend their filamentous structures, called hyphae, out into the soil. These threads explore far beyond the reach of a tree's own roots, unlocking access to water, phosphorus, nitrogen, and other essential minerals. But fungi do much more than simply deliver nutrients. They are the forest's translators, brokers, and messengers. They manage information flow, mediate relationships, and support biodiversity in ways we're only beginning to understand. There are two major types of mycorrhizal fungi, ectomycorrhizal and arbuscular mycorrhizal. Ectomycorrhizal fungi wrap around the outside of tree roots like a glove. They form a sheath that facilitates rapid exchange of water and nutrients. These are most often found in temperate and boreal forests. Think pines, oaks, and beeches. Arbuscular mycorrhizal fungi, on the other hand, actually penetrate the root cells, forming tree-like structures known as arbuscules. These fungi are more common in grasslands and tropical forests, and are essential to the survival of many herbaceous plants. These fungi act like universal plugins, adapting their function based on the species they're connected to. They help stabilize ecosystems, increase drought resistance, and even improve disease tolerance among plant communities. Imagine a forest under stress, perhaps a period of drought. Mycorrhizal fungi step in, transferring water and nutrients from trees with surplus to those in need. When a sapling struggles in the shade, its fungal partner may help it survive until sunlight becomes available. These acts of generosity aren't driven by emotion, but by a system built on interdependence and balance. It's not just plants that benefit either. Fungi enhance soil structure by binding particles together, creating air pockets and improving drainage. This promotes microbial diversity, which in turn contributes to carbon sequestration, storing carbon in soil for long periods. So while we often hear about rainforests as carbon sinks, It's the fungal networks beneath them doing a major part of the work. Fungi also help plants communicate through the underground web, transmitting signals of insect attacks, heavy metals in the soil, or environmental changes. In some cases, the fungal network seems to moderate these messages, amplifying urgent alerts and filtering out noise, like a biological algorithm tuned for survival. And yes, they can be selective. Research suggests that fungi sometimes prioritize relationships with certain trees, especially those that offer more sugars. In this sense, they are not only helpers, but shrewd traders, optimizing their role in a living economy where energy is currency and balance is law. At infinity beyond, we often marvel at galaxies and gravitational waves, at the unseen forces that shape the cosmos. But here on Earth, fungi are our microscopic equivalents, shaping life from the shadows, conducting a silent symphony that makes all other life possible. Yet, for all their brilliance, these networks are fragile. Soil degradation, deforestation, monoculture farming, and pollution can destroy fungal networks in ways that are difficult to reverse. And once the web is broken, trees lose not just their nutrients, but their ability to communicate and coordinate. An invisible intelligence is lost. But there's hope. Ecologists are learning how to reintroduce mycorrhizal fungi into damaged ecosystems. Forest restoration now includes not just planting trees, but inoculating soils with beneficial fungi. It's a rebirth of the underground, a quiet revolution in conservation science. So what can we do as everyday explorers? Support forests, of course, but more than that, support soil. Avoid synthetic fertilizers that harm fungal life. Choose regenerative agriculture when possible, and simply spread awareness that beneath every step in a forest lies a vast, living internet, billions of years in the making. Because in the end, the forest doesn't just grow. It networks, it connects, and it thrives through relationships invisible to our eyes but essential to our survival. So next time you walk beneath a canopy of trees, pause and reflect. There, just beneath the soles of your shoes, is a civilization more ancient than any human city. One built not with stone or steel, but with threads of connection, pulses of cooperation, and quiet, patient wisdom. Forests often appear serene, places of quiet cooperation where trees share nutrients, fungi act as messengers and brokers, and warnings glide silently through the soil and air like leafy telegrams. It's a beautiful vision of unity and harmony, a natural symphony of gentle symbiosis. But let's not get too romantic, because while nature is generous, she also knows how to compete. Beneath all the friendly exchanges and nurturing roots, there is a constant push and pull, a tug-of-war of survival and strategy. Trees are not just neighbors, they are rivals. Rivals for sunlight, for space, for nutrients, for water. Cooperation exists, yes, and we've explored its magic, but it's balanced by an equally powerful force: competition. Sometimes the forest doesn't whisper, it jostles. Let's start with the most obvious resource: light. Sunlight is the lifeblood of trees. Through photosynthesis, trees convert sunlight into sugars, their energy source, and also the currency they use to trade with fungi. But in a forest where the canopy forms a dense green ceiling, light is a rare and precious commodity. Up there, it's a race to the top. This competition begins at birth. Saplings stretch desperately for light, growing tall and thin, often leaning or twisting in bizarre angles just to catch a few extra rays. If they're too slow, they're shaded out by taller neighbors. And without light, they wither. In some forests, over 90% of saplings will die in the shadows. It's a brutal start. Even established trees fight for dominance. Some species grow faster than others, deliberately outpacing slower-growing neighbors to steal their light. In tropical rainforests, Trees develop massive leaves and flexible trunks just to snake their way into sunlit gaps. And it doesn't stop at sunlight. Below the ground, another war is waging for water and minerals. Tree roots spread far and wide, often overlapping and competing with one another. While the fungal network may promote sharing, root systems often compete fiercely, secreting chemicals into the soil to block competitors or absorb nutrients more efficiently. This strategy even has a name: allelopathy. Some trees, like black walnuts, release compounds that inhibit the growth of nearby plants. It's not passive aggression. It's ecological chess, a way to limit competition, control territory, and secure resources for one's own offspring. Even fungi, which we often portray as the selfless connectors of the forest, are selective. They may channel nutrients preferentially to trees that supply them with the most sugars. In other words, if you don't pay up, you don't get the goods. These microscopic middlemen are pragmatic partners, not unconditional givers. And then there's reproduction. Trees may share water, but they do not share pollinators. Species evolve elaborate strategies, from colorful flowers to intoxicating scents, to lure insects, birds, or wind to themselves. The forest becomes a stage of evolutionary advertising, with each plant trying to outshine its competitors. Even the timing of seed dispersal is strategic. Some trees drop seeds early to avoid competition. Others wait for fires, storms, or even animal digestion to activate their growth. Each is trying to carve out a niche, a tiny chance at survival in a crowded world. At Infinity Beyond, we celebrate the awe-inspiring cooperation within ecosystems. But we also recognize the dynamic tension that makes nature so complex. Harmony is not the absence of conflict. It's the result of balance, a never-ending dance between sharing and striving, peace and pursuit. This balance is critical. Without competition, species might grow lazy, over-reliant on partnerships. Without cooperation, forests would fragment, turning into chaotic, disconnected landscapes. But the fusion of both, mutualism and rivalry, creates resilience. And here's the twist. Competition often fuels innovation. Trees under pressure grow stronger roots. They develop smarter seed strategies. They adapt to harsh soil or shifting climate. And in doing so, they teach us an essential truth, that survival doesn't mean crushing others. It means growing smarter, adapting better, and finding the balance between giving and guarding. In fact, recent research shows that some forests maintain dynamic equilibrium, shifting patterns of competition and cooperation based on seasons, stress, and species density. Trees that compete in the spring may share in the drought of summer. It's a flexible system, one that prioritizes survival above ideology. So the next time you walk through a dense woodland and admire its beauty, remember that beneath that beauty lies a wild energy. Every tree is part of a living drama, seeking light, avoiding shade, claiming ground, and sharing just enough to keep the system intact. Nature doesn't pick sides. She creates systems that work. And as we face our own challenges, from climate change to food scarcity, perhaps we can learn from forests not just how to grow, but how to balance. How to be generous, yet resilient. Competitive, yet connected. Because in the end, forests don't just survive, they evolve. Through quiet conversations, strategic rivalries, and unshakable roots. For centuries, the forest was seen as a battleground, a place where trees stood tall in silence, competing fiercely, living and dying in dignified crunches beneath their neighbors. Trees were solitary survivors, locked in evolutionary duels for light and life. But that perspective began to shift, slowly but surely, thanks to a growing number of curious scientists who were willing to dig deeper. Literally. What they discovered, both metaphorically and with actual shovels, fundamentally reshaped our understanding of trees, forests, and even the concept of communication itself. One of the pioneers who led this scientific revolution is Dr. Suzanne Simard. As a young forester working in the dense, damp woodlands of British Columbia, Canada, Dr. Simard began noticing strange patterns. Young trees often thrived beneath certain older trees, not just randomly, but in ways that couldn't be explained by sunlight or soil alone. Some saplings seemed to flourish in areas where, on paper, they should have withered. The traditional model of every tree for itself didn't quite add up, and so she asked a deceptively simple question. Could trees actually be helping each other? To find the answer, she designed an experiment that would make most gardeners raise an eyebrow. She selected two distinct tree species, paper birch and Douglas fir, natural neighbors in the forests of Canada. She planted them together in a controlled forest plot. Then she exposed one of the birches to carbon dioxide labeled with a radioactive isotope, so she could track where the carbon went. What happened next was astonishing. The radioactive carbon didn't just stay in the birch, it traveled underground, through the roots, through the fungal network, and showed up in the Douglas firs nearby. The trees were literally sharing carbon. And this wasn't a one-way exchange. Later, when the Douglas firs were in better health, they returned the favor. The relationship was mutual. This wasn't a forest of isolated competitors. It was a living, breathing community. And just like that, a new understanding was born, one that challenged decades of forestry dogma. Dr. Simard's work showed that trees communicate, collaborate, and form social networks not unlike our own. They share information, balance resources, and support one another across species boundaries. Dr. Simard coined the term mother trees to describe the largest, oldest trees, those that serve as central hubs in this underground web. These trees aren't just feeding their offspring, they're shaping the entire forest. They recognize kin, allocate resources strategically, and influence how the next generation grows. At Infinity Beyond, we often highlight scientists who expand our view of the universe. And Dr. Simard is one such visionary, not by gazing at the stars, but by looking at the roots. She helped us realize that intelligence doesn't have to be fast or noisy. It can be slow, silent, rooted in the ground and spread out through tendrils of cooperation. Her research was met with resistance, of course. Many scientists were skeptical. After all, the idea that trees talk and help each other sounded like science fiction. But as more studies emerged, the evidence grew undeniable. Dozens of peer-reviewed papers now support her findings. And the idea of the Wood Wide Web is becoming mainstream. And it's not just an academic exercise. Dr. Simard's discoveries have major implications for how we manage forests. Clear-cutting, removing all trees from a plot, doesn't just erase vegetation. It disrupts the entire communication system. When mother trees are removed, forests lose their wisdom centers. Saplings struggle more. Biodiversity drops. Recovery slows. But when mother trees are preserved, the forest rebounds faster, guided by the invisible connections still humming beneath the soil. Simard's work also underscores the importance of forest diversity. Birch and fir may be very different trees. One deciduous, the other evergreen, but they benefit each other. Mixed forests, it turns out, are healthier, more resilient, and more adaptive to change than monocultures. That means if we want to preserve forests in a changing climate, we need to protect not just the big charismatic trees, but the relationships between them. Dr. Simard is also passionate about changing how we talk about nature. She believes, and rightly so, that terms like mother, communication, and sharing aren't just poetic metaphors. They reflect real behaviors, measurable and observable, even if they don't follow human logic. Nature doesn't fit neatly into our boxes. Sometimes it takes empathy to see the science. So the next time you walk through a forest, remember the story of Suzanne Simard. Look beyond the trunks. Imagine the networks beneath your feet. Picture carbon flowing between neighbors, warnings pulsing from root to root, wisdom passing down through generations. The forest is alive in ways far deeper than we ever knew, and it took a determined woman with a curious mind to make us see it. We usually reserve the word intelligence for beings with brains. Humans, dolphins, maybe even octopuses. But in recent years, that definition has started to change. A quiet revolution is taking place in biology, and its roots are, quite literally, in the forest. Many scientists now refer to a surprising concept: plant intelligence. Not because trees are conscious in the way animals or humans are, but because they demonstrate behaviors that suggest perception, memory, adaptation, and even decision-making, all without a single neuron. Let's begin with perception. Trees may not have eyes, ears, or skin, but they are constantly sensing the world around them. Through specialized proteins and cellular receptors, they detect subtle shifts in light, temperature, humidity, gravity, soil nutrients, and even airborne chemicals released by neighboring plants. In fact, a tree can know which direction the sun is in, how dry the ground has become, whether it's under threat, or whether a neighbor is being chewed on by a hungry insect. That's right, a tree can sense if its neighbor has been attacked, and it will react accordingly. This awareness gives trees an astonishing ability to adapt. For example, if a young sapling realizes it's in the shadow of a larger tree, it may adjust its growth pattern, not randomly, but deliberately, elongating its trunk more rapidly, redirecting branches toward a light gap, or pausing lateral growth to conserve resources. That's not passive growth, it's reactive growth. Growth with strategy. This brings us to memory. Yes, trees seem to remember. Not like we do, of course. There's no hippocampus in the trunk. But on a cellular level, trees can record past experiences and change their behavior based on them. A tree that has endured a drought may respond more quickly the next time water becomes scarce, closing its stomata sooner to conserve moisture. This isn't just physiological, it's learned resilience. In some experiments, researchers found that trees primed by stress in earlier years showed better responses in future seasons. They were more efficient at producing defensive compounds, faster to react to shade, and even more cooperative with fungal partners. It's a kind of biological conditioning, a forest wisdom coded in cellulose. Let's consider decision-making. Trees have a finite amount of energy, and they must allocate it wisely. Should it go toward growing new leaves? Sending sugars to the roots? Investing in seeds for reproduction? Defending against pests? Or strengthening their fungal connections? These aren't random choices. Trees prioritize, sequence, and sometimes delay actions based on both internal needs and external cues. This ability to make adaptive trade-offs is a hallmark of intelligence, even in its most primitive form. One remarkable study showed that pea plants, not even trees, could predict where light would appear in a Y-shaped maze, choosing the path where they had previously encountered light. With no brain, no nerves, just pure responsive biology. Now scale that up to a 100-foot Douglas fir, and you begin to understand how complex the mind of a forest might truly be. Even reproduction in trees is filled with strategic timing. Some species engage in massed seeding, where all trees in a region release their seeds in a single burst every few years. This overwhelms predators and ensures more seeds survive. But what's fascinating is how trees know to synchronize. It seems to be a combination of stored energy, environmental cues, and, possibly, chemical communication. It's not conscious in the human sense, but it's definitely not random. At Infinity Beyond, we celebrate the strange and wonderful boundaries between science and wonder, and this is one of them. Tree intelligence blurs the line between biology and what we might call behavior. It asks us to rethink life, not as a hierarchy with humans at the top, but as a web of living, learning systems, each operating on its own timescale. Of course, the idea of intelligent plants was once dismissed as pseudoscience. Early researchers in the 1970s who proposed it were often ridiculed. But modern molecular biology, combined with advances in ecology and neuroscience, is painting a more nuanced picture. No, trees don't think. But yes, they do respond, remember, plan, and adapt. And that's a kind of thinking, just not the kind we're used to. There's something deeply humbling in this idea. While we build supercomputers and AI, forests have been running slow, organic algorithms for hundreds of millions of years. They adapt without urgency. They learn without lectures. They coordinate without meetings. And they do it in a way that sustains entire ecosystems, and ultimately, us. So the next time you're near a tree, pause. Gently press your hand to its bark. Realize that you are in the presence of a being that senses you, even if you can't perceive it. A being that has seen droughts, storms, and fires, and survived. A being that is part of a community, rooted in memory and awareness, reaching for the light in more ways than one. Long before forests blanketed the continents, long before even the first dinosaurs stirred in the undergrowth, life on Earth was ruled by the oceans. The earliest life forms, simple algae, bacteria, and tiny marine organisms, thrived in the protective embrace of water. But around 500 million years ago, something extraordinary began to unfold. At the edges of these ancient seas, a few brave pioneers crept toward land. These weren't trees, flowers, or even ferns. They were primitive, leafless plants, small and humble, resembling moss or liverwort more than anything we see today. They had no roots, no stems, and certainly no wood. On their own, their chances of surviving the brutal conditions of early Earth were slim. Why? Because the land was harsh and unforgiving. The soil, what little of it there was mostly raw, undecomposed rock. Essential nutrients like phosphorus and nitrogen were locked away, inaccessible without tools. Rainwater came and went, with no plant roots to soak it up. And worst of all, there was no protective ozone layer. Ultraviolet radiation blasted the land with relentless intensity. So how did life on land begin? Enter the fungi. Fungi had already been thriving on dry land for millions of years. Unlike plants, they didn't need sunlight to survive. They broke down rock, formed partnerships with bacteria, and wove themselves into the soil using fine filamentous threads known as hyphae. These early fungal networks were like nature's first explorers, mapping, dissolving, and transforming Earth's crust. When the first land plants arrived, the fungi were ready. And what happened next was one of the most important partnerships in the history of life on Earth. Fungi offered the plants something invaluable: access. They tapped into water, minerals, especially phosphorus, and transferred these essentials directly into the cells of the plants. In exchange, the plants offered something fungi couldn't produce on their own: sugars made through photosynthesis. It was a deal struck in silence, in the shadows of time, but it changed everything. This alliance, known as the mycorrhizal relationship, gave early plants the boost they needed to colonize land. They could now grow taller, spread wider, and survive droughts. Over time, they evolved roots, leaves, and vascular systems. They became ferns, then trees, then vast forests, and with them came insects, animals, and eventually, us. Without fungi, there would be no forests, no flowers, no food chains, no humans. Let that sink in. The lush green world we live in today, the one that provides oxygen, food, shelter, and shade began with a collaboration between two of life's earliest forms, plant and fungus. What's even more incredible is that this partnership didn't stop in the past. It's still happening right now under your feet. Over 90% of land plants today still form mycorrhizal relationships. That includes towering redwoods, flowering plants, grasses, and even the crops that feed our species. These fungi live in and around the roots, extending their hyphae into the soil like microscopic fishing lines, absorbing nutrients, retaining moisture, and transferring information. At Infinity Beyond, we love exploring the cosmos and unraveling the mysteries of galaxies and black holes. But this is a mystery that unfolded right here on Earth, a biological story so ancient and profound it could rival any cosmic origin. Let's break this down with a bit more precision. These early fungi, likely from the group called Glomeromycota, were masters of survival. They could thrive in low-nutrient environments and formed arbuscular mycorrhizae, which penetrated plant root cells and created intricate exchange systems. In fact, scientists have discovered fossil evidence of these partnerships dating back over 400 million years. These fossilized root impressions show fungal structures inside, a silent testimony to the world's first underground economy. And it wasn't just nutrients being traded. Recent research suggests that even ancient fungi may have played a role in regulating water flow, protecting plants from pathogens, and helping them adapt to the wildly fluctuating conditions of primitive Earth. In short, fungi weren't just helpful, they were essential. Today, these ancient partnerships have evolved into complex ecosystems. Forests are built upon this alliance. Coral reefs have their own symbiotic arrangements, and even humans have borrowed the idea, using fungal relationships to improve agriculture through mycorrhizal inoculation of soils. So, the next time you look at a blade of grass, a flower, or a tree, remember that beneath it lies a story billions of years old. A story not of conquest, but of collaboration. The land wasn't conquered by plants. It was co-inhabited, co-developed, co-evolved through a silent handshake of sugars and minerals. A handshake we're only beginning to truly understand. And perhaps, as we face our own future on this planet, we should take a lesson from this ancient alliance. Survival doesn't always come from being the biggest or the strongest. Sometimes it comes from forming the right partnerships. Cutting down a tree might seem like a simple act. One trunk removed, one shadow gone, one space cleared. But in the complex world of the forest, the impact is far deeper than what the eye can see. When you remove a tree, especially an old one, you're not just subtracting a piece of wood from the landscape. You're erasing a hub in a living network. You're silencing a voice in the underground conversation. In fact, you might be removing a mother tree, an elder in the forest's underground social system. And with that comes profound consequences. As we've learned throughout this journey, mother trees are more than just tall, old organisms. They are information centers, resource banks, and guardians of regeneration. Their roots are deeply connected to the microcosm of younger trees around them, often intertwined through the mycorrhizal fungal network we explored in previous episodes. When one of these giants is cut down, it doesn't merely vanish. It leaves a void, a kind of silence in the soil. Nearby saplings may suddenly lose their strongest source of carbon, water, or mineral nutrients. Trees that once relied on warning signals or guidance from the elder are now isolated. The communication lines, carefully maintained through seasons of growth and stress, are broken. The forest's resilience to stress begins to fray. Think of it like removing a keystone from an arch. The rest of the stones might stand for a time, but the entire structure becomes fragile. One strong wind, one long drought, one insect outbreak, and everything begins to collapse. Modern forestry has started to recognize this. A method known as retention forestry is emerging in many regions, especially in Europe and North America. It's based on the principle of leaving some mother trees behind during logging operations. These trees help maintain the underground network, support the next generation, and preserve biodiversity. Retention forestry doesn't just protect soil structure, it protects memory. Yes, memory. Because forests are not just physical spaces, they are biological archives. The DNA in their roots, the chemical signals in their mycorrhizal networks, these hold the wisdom of generations. When we cut all trees indiscriminately, we erase that archive. Some researchers have even found that forests with intact mother tree networks recover more quickly after wildfires or human disturbance. Their root systems stabilize the soil. Their fungal partners re-establish connections. Their presence fosters a return to equilibrium far faster than in completely cleared areas. This knowledge is changing how we define sustainability. Sustainable forestry isn't just about planting new trees after cutting old ones. It's about maintaining the social structure of the forest. Trees grow, but relationships, true, deep ecological relationships, take decades or centuries to form. And then there's the emotional side, because forests aren't just science. They are stories. They are sacred to cultures around the world. From indigenous communities in Canada to rainforest dwellers in the Amazon, trees are seen as ancestors, spirits, teachers, and science now supports what these traditions have long held true, that forests are communities, not commodities. So what can you and I do? Support rewilding projects that reintroduce native species and leave legacy trees untouched. Advocate for smarter forestry regulations that prioritize retention and biodiversity over profit. Choose wood and paper products from certified sustainable sources that respect ecological networks. Plant native trees. And when possible, plant them in clusters to mimic community formation. Educate others. Share what you've learned about mother trees, fungal networks, and plant communication. At Infinity Beyond, we're passionate about uncovering not just the stars above, but the worlds within. And the forest is one of the most intricate, inspiring worlds we've explored yet. It's a world where silence speaks, where roots remember, and where every tree, no matter how small, plays a role in something far larger. So the next time you see a towering tree, pause. Recognize that you're not just looking at a plant. You're standing in the presence of a network node, a mentor, and a memory keeper. And if that tree falls, the echo won't just be heard in sound, it will be felt in the soil, in the seedlings, in the songs of birds, and in the stories of science and spirit alike. We've talked about the beginning of the universe, the Big Bang, and speculated about its distant end. But now, let's ask the most forbidden question in all of cosmology. What happened before the Big Bang? It's a question that has haunted thinkers, philosophers, and physicists for centuries. It dares to look behind the curtain of time itself, to ask if there was a before there was time. At first glance, it sounds like nonsense. The Big Bang wasn't just the beginning of matter and space. It was the beginning of time as we know it. Asking what came before is like asking what's north of the North Pole. But modern physics is not so quick to dismiss the question. In fact, some of the boldest scientific theories of our time suggest that the Big Bang may not have been the true beginning at all, but rather a transition, a bounce, or a doorway from something else. Let's explore the leading ideas. 1. The quantum foam. At the smallest scales imaginable, below atoms, protons, and even quarks, lies the bizarre world of quantum mechanics. Here, the fabric of space-time is not smooth, but a jittery, frothing sea of uncertainty known as quantum foam. Some theories suggest that even nothingness is unstable. Tiny fluctuations can spontaneously pop particles, and even miniature black holes into existence, and then, just as quickly, annihilate them. According to this view, the Big Bang could have emerged from a random quantum fluctuation. One moment, there was nothing. The next, a universe, expanding rapidly, driven by vacuum energy. In this model, there is no before, only an eternal sea of probability, from which our universe happened to emerge. 2. The bounce, a universe before ours. Imagine if the Big Bang wasn't the first bang. The Big Bounce theory suggests that our universe is the latest in a cosmic cycle, a rhythmic breathing of space-time. A previous universe may have collapsed in a big crunch, only to bounce back and create ours. In this scenario, there was a universe before the Big Bang, with its own stars, galaxies, perhaps even life. And ours is just the next verse in an eternal cosmic song. Some models of quantum gravity support this, suggesting that space-time resists complete collapse, allowing for a rebound instead of a singularity. If true, this would mean we're living in a universe with a past far longer than 13.8 billion years. 3. The multiverse. Another contender is the multiverse. The idea that our universe is just one bubble in a vast cosmic foam of universes. In this view, the Big Bang was not the beginning of everything. It was the beginning of our local region of space-time. There may be countless other universes, each with their own laws of physics, dimensional structures, and timelines. Some may be timeless. Some may collapse instantly. Others may live for trillions of years. The implications are staggering. We might be one spark in an eternal fireworks show, the flicker of an infinite creation engine. Some string theory models, such as eternal inflation, support this concept. They propose that inflation, the rapid expansion that followed the Big Bang, happens constantly in different pockets of the larger meta-universe. Our universe could be just one bubble among many. 4. No time at all. Perhaps the most humbling idea is this: time itself may be an illusion. According to some physicists, time is not a fundamental property of the universe, but an emergent phenomenon, something that arises only under certain conditions, like temperature or pressure. If that's true, then before the Big Bang is a meaningless question. There was no before this, not because it's forbidden, but because time didn't exist in the way we understand it. The cosmos may be timeless at its core, with the arrow of time emerging only after the Big Bang when entropy began to increase. This flips our understanding upside down. The Big Bang didn't happen in time. Time happened in the Big Bang. Can we ever know? Right now, the question of what came before the Big Bang remains unanswered, but not unaskable. New tools, like the James Webb Space Telescope, are helping us look deeper into the earliest light of the universe, examining the structure of galaxies, the background radiation, and the chemical fingerprints left by ancient stars. Some scientists are even searching for echoes, subtle imprints in the cosmic microwave background that could reveal signs of a previous universe. If the multiverse is real, we may someday detect collisions between our bubble and others, leaving scars on the sky. And if time is emergent, then future physics may unlock the quantum structure of space-time itself, peeling back the veil on reality's deepest layer. Until then, we wonder. And perhaps that's what makes us truly cosmic. Not just our atoms or our stardust, but our capacity to question, to imagine, and to seek answers that lie beyond time itself. Here on Infinity Beyond, we believe the best questions don't have easy answers, but they open the mind, stretch the soul, and bring us closer to the truth. The Big Bang was not the end of the mystery. It was just the start. We've traveled from the origin of the universe to the possibility of simulated realities. But today, we're going to unravel something even more elusive, something we all experience, yet rarely understand. Time. We treat time as constant. We schedule our lives by it. We age through it. But what if time, as we know it, isn't real? What if it's not a river flowing from past to future, but a dimension just like space, one we move through or even imagine? This idea isn't just poetic. It's rooted in cutting-edge physics, mind-bending thought experiments, and a bold claim that has baffled scientists and philosophers alike. Time might be an illusion. What is time really? From a young age, we're taught that time passes. Seconds tick by. Events occur in a sequence: before, now, after. But in physics, things are not so simple. Einstein's theory of relativity shattered the idea of absolute time. He showed that time is relative. It moves differently, depending on your speed and gravitational field. Clocks tick slower on a spaceship near the speed of light. They tick faster at the top of a skyscraper than at the bottom. This means time is not fixed. It's flexible. It's part of the fabric of the universe, intertwined with space as space-time. So what does that mean? It means the past, present, and future may all exist simultaneously, like frames of a film reel already there. We just experience them one at a time. The block universe. Time as a dimension. Enter the block universe theory. In this model, the universe is a four-dimensional block. Length, width, height, and time. All events, from the birth of stars to your breakfast this morning, coexist in this block. There is no flow of time, no universal present. Your entire life, every moment you've lived and will live, is frozen in the block. You are just a 4D being, extended in space-time, experiencing slices of yourself moment by moment. It's a radical idea, but one that makes sense of relativity. It also means there's no objective now. Your present may be someone else's ancient past. Time is local, not universal. Consciousness and the illusion of flow. So why do we experience time as flowing? Some neuroscientists believe the sensation of time moving forward is created by memory and causality. Your brain stores previous events and strings them into a narrative. This gives you the illusion of a moving present. In other words, you're not moving through time. Your consciousness is creating the sensation of motion. It's like watching a flipbook. Each page already exists, but your mind animates the illusion. Entropy and the arrow of time. But hold on. Doesn't time clearly move forward? Eggs don't unscramble. Smoke doesn't unburn. We age, we die. This is the arrow of time. And it's dictated not by physics, but by thermodynamics. Specifically, the second law of thermodynamics, entropy. The measure of disorder always increases. In the past, things were more ordered. Over time, chaos grows. That's why time feels like it flows. But what if entropy is not a rule, just a statistical trend? What if the direction of time is not fundamental, but emergent? Some physicists believe the universe began in a low entropy state, highly ordered. And as entropy increases, we get the illusion of time moving forward. In other words, time might just be what entropy looks like from inside the system. Quantum physics. Superposition of timelines? Let's get even weirder. In quantum mechanics, particles can exist in multiple states at once, a phenomenon known as superposition. Only when observed do they collapse into a single outcome. Could time itself be a kind of superposition? Could the future and past exist in a smeared-out cloud, and your consciousness collapses one timeline into reality as it moves? This idea has sparked theories of retrocausality, where future events influence the past. It's controversial, but quantum physics has already proven that reality is far stranger than we expected. Could time be hacked? If time is a dimension, could we travel through it? Einstein's equations allow for time dilation, moving forward in time. A spaceship near light speed could travel 1,000 years into Earth's future in a matter of days from its perspective. But moving backward in time is trickier. Some solutions to Einstein's equations, like rotating black holes or wormholes, allow for closed time-like curves or theoretical time loops. But they also introduce paradoxes, like the classic grandfather paradox. Still, scientists haven't ruled time travel out completely. In fact, projects like the Laser Interferometer Gravitational Wave Observatory, LIGO, are exploring how ripples in space-time could offer insights into temporal anomalies. Time might be flexible, even navigable. Why it matters. So, what does all this mean for you? It means the moment you're living in is not the only one that exists. Your past is still there. Your future might already be written, or constantly unfolding based on quantum probabilities. It also means death may not be an erasure, but a transition in your block of space-time. You will always have existed in the geometry of the cosmos, and that is strangely comforting. Here on Infinity Beyond, we believe understanding time isn't just a physics question, it's a spiritual one. Because if time is not what we think, then neither are we. Among all the wonders scattered across the cosmos, few captivate the imagination and terrify the soul, quite like black holes. These dark monsters of gravity defy our understanding. They are born in the depths of stars, consume anything that comes too close, and bend space and time to their will. For decades, they were treated as the ultimate dead end, places where physics breaks down. But what if that's not the whole story? What if black holes are not the end, but a beginning? Today, we're diving into one of the most thrilling and controversial ideas in theoretical physics: black holes as possible gateways to other universes. What is a black hole? Let's start with the basics. A black hole forms when a massive star collapses under its own gravity. The core compresses into a point of infinite density, a singularity, surrounded by a boundary called the event horizon. Cross that threshold, and there's no turning back. Not even light can escape. Inside, space and time are warped beyond comprehension. Gravity becomes so strong that our current laws of physics, general relativity, and quantum mechanics are no longer compatible. It's the cosmic equivalent of "here be dragons." But the real mystery lies beyond the event horizon, a region we cannot observe directly, yet which may hold secrets to the multiverse, wormholes, and even the rebirth of space and time. Do black holes destroy or transport? For decades, the assumption was that anything falling into a black hole, a planet, a star, your favorite spacecraft, would be crushed into nothingness. But new theories challenge that idea. One of the boldest proposals comes from Einstein and Rosen back in the 1930s. They theorized that the singularity inside a black hole might not be a dead end, but instead a bridge, now called an Einstein-Rosen bridge, or more famously, a wormhole. This hypothetical tunnel could connect distant points in our universe, or even open into an entirely different universe. Imagine stepping into the jaws of a black hole and emerging on the other side, reborn in a new reality. The white hole hypothesis. A related idea is the white hole, the theoretical opposite of a black hole. Where black holes pull in matter, white holes push it out. They cannot be entered from the outside, and anything within must eventually be expelled. Some theories suggest that what falls into a black hole in one universe may be ejected from a white hole in another. In this view, black holes are not just destroyers. They're cosmic engines, recycling matter and energy across dimensions. Black holes and the Big Bang. Now, here's where it gets even weirder. Some physicists, including those working in loop quantum gravity and string theory, propose that our entire universe may have been born from the core of a black hole in another universe. That's right, the Big Bang itself might have been the explosive emergence of space-time through a white hole, the birth canal of another reality. In this model, black holes don't just warp space-time, they generate it. Every black hole in our universe could be seeding new universes, creating a cosmic family tree of realities, with each branch representing a new Big Bang. The holographic principle. How could this be possible? Enter the holographic principle, a mind-blowing idea from string theory suggesting that all the information that falls into a black hole is not destroyed but encoded on its surface, the event horizon, like pixels on a screen. This means the inside of a black hole might be holographically projected from the boundary itself. It also suggests that black holes may not truly erase information, only hide it in ways we can't yet decode. If we could crack the holographic code, we might learn not only what's inside black holes, but whether they're portals to somewhere else. Hawking radiation and black hole evaporation. But don't black holes eventually vanish? Yes. According to physicist Stephen Hawking, black holes slowly emit energy through quantum processes near the event horizon, a phenomenon now known as Hawking radiation. Over trillions of years, a black hole can shrink and evaporate completely. But where does the information go? This question, the black hole information paradox, remains one of the greatest unsolved problems in theoretical physics. Some theories suggest that the information is stored on the event horizon. Others propose it's released at the end, or carried into a baby universe on the other side. Either way, it keeps the door open to the idea that black holes don't just end reality, they connect it. Wormholes, stable or not. If black holes can form wormholes, could we ever travel through them? Theoretically, yes, but it's complicated. Wormholes require exotic matter, with negative energy density, to remain stable and open. Without it, they would collapse instantly. So far, we haven't discovered exotic matter in usable amounts. But concepts like the Alcubierre drive and quantum field experiments suggest it may not be impossible. In the distant future, civilizations might learn to harness black holes, open wormholes, or even engineer them. Until then, we search. Why it matters. This isn't just a question about space monsters. It's about the fundamental nature of reality. If black holes can lead to other universes, then our cosmos is not an isolated bubble. It's part of a grand multiversal network stitched together by gravity, entropy, and information. It means death, even cosmic death, is not final. It's a gateway. And perhaps, someday, we'll find the courage, or the technology, to pass through. Here on Infinity Beyond, we ask the impossible questions and follow them wherever they lead, even into the heart of a black hole. The universe is vast, mysterious, and often stranger than fiction. We've explored galaxies, black holes, time illusions, and even simulated realities. But what if the cosmos itself carries scars? Remnants of creation, stretching across space, thinner than atoms, but heavier than mountains. These aren't mythological ideas. They're theoretical objects in high-energy physics called cosmic strings. These ultra-thin, ultra-dense filaments might be the very cracks in space-time, left over from the Big Bang. And if they exist, they could hold the key to understanding the birth of the universe, gravitational waves, and even the structure of reality itself. Let's unravel this idea. What are cosmic strings? Cosmic strings are not strings like spaghetti or shoelaces. They're one-dimensional topological defects, theoretical structures predicted by certain grand unified theories of particle physics. Think of them as hairline fractures in the fabric of the universe, formed as the universe cooled and expanded in its earliest moments, much like cracks forming in ice as water freezes. These defects would be infinitely long, or looped into massive closed rings. But here's the kicker. They'd be thinner than a proton, yet contain more mass per centimeter than Mount Everest. Their gravitational pull would be so intense they could warp space-time and act like cosmic lasers, bending light and slicing through matter. Birth of strings, a frozen relic. To understand where they come from, imagine the universe in its first trillionths of a second. It was unimaginably hot, dense, and chaotic. As it expanded, it underwent phase transitions, much like how water turns to ice or steam condenses into water. During these transitions, the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, separated. But this process wasn't smooth. In some regions, mismatches in symmetry occurred, creating defects in the field. These defects could stretch across the cosmos, forming cosmic strings. They're not made of atoms or particles, but of raw energy, frozen in a stable configuration. Once formed, they would last for billions of years, perhaps until today. How would we detect a cosmic string? Detecting a cosmic string would be like finding a thread thinner than a proton, stretching across galaxies. Fortunately, they leave behind unique signatures. 1. Gravitational lensing. Cosmic strings bend light in a very specific way. If light from a distant galaxy passes near a string, it would be split, creating two identical images side by side, like a mirror. This lensing would be unlike anything seen from galaxies or black holes. 2. Gravitational waves. Cosmic strings can form loops, which oscillate and decay by emitting gravitational waves, ripples in the fabric of space-time. These waves would have a distinctive frequency, different from those created by black hole mergers. Detectors like LIGO, Virgo, and future instruments like LISA might one day pick them up. 3. Pulsar timing arrays. Millisecond pulsars, rotating neutron stars, emit regular radio pulses. If a cosmic string passed near Earth, the timing of these pulses would shift, revealing its presence. Projects like Nanograv are already studying such data and have recently found signals that could be consistent with cosmic string activity. Why cosmic strings matter? You might be wondering, why care about some invisible line in space? Because cosmic strings are a direct window into the first moments of the universe. They're a relic of symmetry breaking, a moment when the universe chose its fundamental laws. Studying them could confirm or rule out entire branches of particle physics, including grand unified theories and superstring theory. And here's where it gets cosmic. Some theorists believe that superstrings, the building blocks of the multiverse, in string theory, could manifest as cosmic strings in our 3D universe. In that sense, cosmic strings might not just be leftovers. They could be signposts from higher dimensions. Could we interact with one? Let's say we found one. Could we study it? Touch it? Probably not. At least not safely. A cosmic string's gravitational energy would be so immense that passing near it could sever atoms, tear apart planets, or disrupt time itself. But theoretically, a stable loop of cosmic string could become a gravitational wave antenna, or even a form of propulsion. Some science fiction writers have imagined wrapping a spacecraft around a cosmic loop to generate near-light-speed travel. Others suggest strings could stabilize traversable wormholes or generate closed time-like curves, allowing time travel. Though purely speculative, the implications are tantalizing. What if they don't exist? It's important to remember, we haven't observed a cosmic string yet. Many surveys have searched the sky for the telltale signs. Double images, gravitational lensing arcs, and unusual background radiation distortions. So far, nothing conclusive. But the absence of evidence is not evidence of absence. Cosmic strings may be rare, Or they may exist on scales or energies just beyond our current reach. With more sensitive telescopes and gravitational wave detectors coming online in the next decade, we may finally glimpse one, and with it, a thread back to the beginning of time. Final thought. The universe may be a finely woven tapestry. Galaxies, stars, planets, all hanging delicately on threads we cannot see. Cosmic strings are more than a theoretical curiosity. They are a bold reminder that the universe carries history in its very fabric. They whisper of a time when everything was energy, when reality crystallized into the world we know, and perhaps of worlds we don't yet understand. Here on Infinity Beyond, we follow those whispers, all the way to the edge of physics. Because sometimes, it's in the smallest threads that the biggest truths are hidden. For centuries, humanity believed the universe was static, that the stars were fixed, and space itself unchanging. But discoveries in the 20th century shattered that illusion. We now know the universe is expanding. Galaxies are moving away from each other, as if space itself is stretching. But in 2008, astronomers discovered something even more mysterious. Something that doesn't fit any model of cosmic expansion. A force, or motion, that seems to pull entire galaxy clusters in one direction. It's called the dark flow, and it might just be evidence that something beyond our observable universe is influencing ours. Let's dive into this cosmic enigma. The discovery of dark flow. The story begins with NASA's Wilkinson Microwave Anisotropy Probe, WMAP, a satellite launched to map the cosmic microwave background, CMB, the leftover radiation from the Big Bang. By analyzing the CMB, scientists hoped to better understand the early universe, but they noticed something odd. Clusters of galaxies. Some of the largest structures in the universe were drifting at high speeds in a specific direction, independent of the Hubble flow, the standard cosmic expansion. This motion wasn't random, it was coherent, as if thousands of galactic systems were being pulled by something outside the visible universe. They were moving toward a patch of sky between the constellations Centaurus and Vela, at over 2 million miles per hour. This became known as the dark flow. What could cause it? There's no consensus yet, but scientists have proposed several wild and exciting possibilities. 1. A massive structure beyond the observable universe. The most straightforward explanation is also the most unsettling. Something exists beyond the edge of the observable universe, something massive enough to tug on galactic clusters. This could be a supercluster of matter, an enormous void, or even a region of space-time with different properties. But if true, it would mean that our observable universe is just a small bubble within a much larger and stranger structure. And that brings us to 2. The multiverse hypothesis. What if the dark flow isn't caused by something in our universe, but by another universe entirely? According to the multiverse theory, our universe is just one of many, each with its own laws of physics. Some inflationary models suggest that during the birth of the cosmos, different regions of space inflated into their own universes, bubbles floating in a higher dimensional space. If one of these universes passed close to ours, it could gravitationally influence our matter, pulling galaxies toward it. That's right, the dark flow could be the footprint of a neighboring universe. 3. A flaw in our cosmological models. Of course, there's a more conservative idea. We might be misinterpreting the data. The motions we observe could result from local inhomogeneities, massive nearby structures we don't yet fully understand, like the Great Attractor or the Shapley supercluster. Or it might be an artifact of how we measure galaxy velocities. If that's true, then the dark flow isn't real, just a mirage created by gaps in our understanding. But the evidence remains intriguing and hasn't been entirely explained away. Why it's a big deal. If the dark flow is real, it changes everything. It means the cosmological principle, the assumption that the universe is isotropic and homogeneous on large scales, might be wrong. It suggests the universe isn't smooth and uniform. It's structured, influenced by forces and realms beyond what we can see. It could even provide the first empirical evidence for the multiverse, something that was, until now, purely theoretical. And it forces us to rethink our position in the cosmos. We're not just floating in space. We may be drifting through a vast sea of unseen forces, unknowable neighbors, and ancient gravitational tides. Where we stand. Today. Since the initial discovery, additional surveys have tried to confirm or disprove the dark flow. Some support the finding. Others suggest it's a statistical fluke. More advanced missions, like Planck, didn't find strong confirmation, though they didn't rule it out entirely. The debate is ongoing, but future projects, such as the Euclid Space Telescope, Vera C. Rubin Observatory, and Nancy Grace Roman Telescope, will map the cosmos with the unprecedented precision. They could finally resolve the mystery, or reveal something even stranger. Could we ever detect what's beyond? By definition, the observable universe is limited. Light from beyond 46 billion light-years hasn't had time to reach us since the Big Bang. But gravitational effects don't follow the same rules. If something massive exists just beyond our cosmic horizon, its gravitational tug can still affect matter here. That's what makes the dark flow so compelling. It might be our only window into what lies beyond. And if there's structure, or even life, in a universe adjacent to ours, dark flow may be its distant whisper. Final thought. The universe has a way of revealing its secrets slowly, in shadows, in subtle nudges, in patterns that seem almost too strange to be real. The dark flow is one of those secrets. It may turn out to be an illusion, a measurement error, or a glimpse into the most profound truth we've ever faced, that our universe is not alone. Here on Infinity Beyond, we follow the signs, no matter how faint, in search of that truth. Because sometimes it's the invisible forces that tell the greatest stories. When we think of space, we often imagine a vast emptiness scattered with stars, galaxies, and glowing nebulae. But the truth is far stranger. Between the threads of the cosmic web, those long filaments of galaxies and dark matter, lie enormous regions of almost nothing. They are called cosmic voids, and they are the emptiest places in the known universe. No stars, no galaxies, just an ocean of darkness stretching across hundreds of millions of light years. But here's the question. If these regions are so empty, why do they matter? And what could be lurking in the vast silence? Let's journey into the void. What are cosmic voids? Cosmic voids are the giant underdense regions between the large-scale structures of the universe. While they're not completely empty, they have far fewer galaxies, stars, and matter than average. Imagine the universe as a sponge. The web, or foam, is where galaxies cluster. The bubbles in between, that's the void. Voids are immense. The average void spans about 30 to 300 million light-years across. The largest ever found, the Boötes void, is nearly 330 million light-years wide and contains very few galaxies within its volume. That's more than 250,000 Milky Ways wide and almost completely dark. But why are they there? How voids formed. In the early universe, matter wasn't spread evenly. Quantum fluctuations seeded regions of slightly higher and lower density. Over billions of years, gravity amplified the denser regions, pulling matter inward to form stars, galaxies, and clusters. The underdense areas? They were left behind, expanding faster than average, growing into vast voids as the rest of the universe condensed into structure. In a way, the voids are the cosmic leftovers. the forgotten spaces between the visible. But make no mistake, these voids aren't irrelevant. They could be the key to understanding the universe itself. Why voids matter? Cosmic voids are sensitive probes of dark energy, the mysterious force driving the acceleration of the universe's expansion. Because voids expand faster than denser regions, they exaggerate the effects of dark energy. By studying their size, growth rate, and shape, scientists can better constrain models of cosmic acceleration. Voids also help test general relativity and alternate theories of gravity. In low-density environments, modified gravity theories predict different behaviors than Einstein's equations, making voids perfect testing grounds. And then there's the mystery of what we're not seeing. The cold spot. Mystery. In 2000, data from the Wilkinson Microwave Anisotropy Probe, WMAP, revealed an unusually large and cold region in the cosmic microwave background, the oldest light in the universe. This region, dubbed the CMB cold spot, was cooler than expected and too large to be explained by standard models. Later observations by the Planck satellite confirmed the anomaly. One explanation? A supervoid, a colossal underdensity stretching over 1.8 billion light-years, may lie in that direction, draining energy from photons as they pass through. But the numbers still don't add up completely. Some physicists speculate the cold spot could be a hint of something deeper, perhaps a collision with another universe, or a topological defect from the early universe. Either way, voids are becoming a focal point in the search for cosmic anomalies. Could anything exist in a void? Surprisingly, yes. Voids aren't completely empty. They contain gas, dark matter, and isolated galaxies, sometimes called void galaxies. These galaxies are often smaller, less evolved, and form in isolation, unshaped by interactions or mergers common in denser environments. Studying them gives scientists a glimpse into how galaxies evolve without external interference, like observing cosmic evolution in a lab. Voids may also be home to faint dark galaxies, composed mostly of dark matter with little or no visible stars. Some theories even suggest voids could contain exotic physics, topological defects, remnants of symmetry, breaking in the early universe, or even cosmic strings hiding in plain sight. A gateway to the unknown? Here's where science blurs with speculation. Because voids are so large and mysterious, some theorists wonder, could they be gateways? One hypothesis is that voids represent more than just absence. They could be interfaces between different quantum vacuums, or even regions where the fabric of space-time is thinner. In some inflationary models, voids may be where the energy of the universe was lowest, possibly hinting at different physical constants, alternate realities, or weak spots in the cosmic field. Others suggest voids could act like cosmic insulation, expanding to isolate regions of the universe from one another. Could we travel through one? Could something else come from one? We don't know. But the questions are getting louder. What's next in void research? Upcoming missions like Euclid, the Nancy Grace Roman Telescope, and the Vera C. Rubin Observatory will map cosmic structures in greater detail than ever. They'll reveal the shapes, sizes, and motions of voids, testing the influence of dark energy and gravitational laws across vast distances. Simulations like Illustris and Millennium are modeling the evolution of voids and how they interact with galaxies and dark matter. The goal? To use emptiness as a tool, to learn what we can't from matter alone. Because sometimes the best way to understand the universe is to study what's not there. Final thought. Cosmic voids are nature's quietest regions, silent, dark, and seemingly lifeless. But in that stillness lies potential, clues to the origin of the universe, tests for our deepest theories, and possibly a path to answers we haven't even thought to ask. Here, on Infinity Beyond, we believe even the void has a story to tell. And we're here to listen. We look at the night sky and see stars, planets and galaxies, spread out in every direction like glowing jewels on black velvet. But beyond what we can see lies a deeper, more profound question. What is the shape of the universe itself? Is it curved like a sphere? Is it a saddle-shaped expanse? Or is it perfectly flat, stretching into infinity? The geometry of space may sound abstract, but it holds the key to understanding the origin, structure, and fate of everything. Let's explore the possible shapes of the cosmos and what each one means for our place in the grand design. What do we mean by shape? When we talk about the shape of the universe, we're referring to the geometry of space-time on the largest scales, billions of light-years across. Just like a sheet of paper can be flat, folded, or warped, space itself can bend and curve. The shape of the universe is determined by its density of matter and energy, especially dark energy and dark matter. There are three main possibilities, each with wildly different implications. 1. A flat universe. In a flat universe, parallel lines never meet. Geometry works exactly as we learned in school. The angles of a triangle add up to 180 degrees, and space extends forever. This doesn't mean the universe is two-dimensional or pancake-shaped. It means space is flat in 3 dimensions. According to the most recent data from the Planck satellite and WMAP, the universe appears to be flat to within 0.4% accuracy. This implies a perfect balance between the gravitational pull of matter and the outward push of expansion, a cosmic equilibrium. In a flat universe, the universe expands forever, but slows asymptotically. Light travels in straight lines. The cosmic microwave background, CMB, appears uniform and evenly spaced. But flat doesn't mean finite. A flat universe could still be infinite in extent. This is the current leading model in cosmology. 2. A closed universe, spherical. Imagine the surface of a sphere, but in 3 dimensions. In this model, the universe has positive curvature. Like the Earth, it's finite but unbounded. You could travel in one direction long enough and return to your starting point, assuming space didn't expand faster than you could travel. In a closed universe, parallel lines eventually meet. The angles of a triangle add up to more than 180 degrees. Light bends over long distances. The universe might one day stop expanding and begin to contract, ending in a big crunch. Some early observations hinted at this possibility, but more precise measurements have increasingly favored flatness. Still, small curvature can't yet be ruled out entirely. 3. An open universe, hyperbolic or saddle-shaped. Now imagine a Pringle chip or a horse's saddle. An open universe has negative curvature. It expands forever and accelerates faster over time. In this model, parallel lines diverge. Triangles add up to less than 180 degrees. The universe has no boundaries and is infinite in all directions. In a negatively curved universe, the cosmos would look increasingly distorted at extreme distances. This shape predicts a colder, more diffuse universe over time, ultimately leading to heat death and endless entropy. How do we measure the shape? To determine the shape of the universe, scientists use multiple tools. 1. The cosmic microwave background, CMB, as the CMB provides a snapshot of the universe just 380,000 years after the Big Bang. By measuring the angular size of temperature fluctuations, scientists can infer curvature. If the fluctuations appear larger than expected, space is curved positively. If smaller, it's negatively curved. If they match predictions, flat. Planck's data shows fluctuations exactly as expected in a flat universe. 2. Baryon acoustic oscillations, BAO. These are ripples in the distribution of galaxies, caused by sound waves in the early universe. By measuring the distance between galaxies at different redshifts, scientists can detect curvature. So far, BAO data aligns with a flat model. 3. Type Ei supernovae. These standard candles allow astronomers to measure distances and expansion rates. By comparing observed brightness with predicted brightness, curvature effects can be detected. Again, flatness remains consistent with observations. Could the universe have a more complex shape? Yes, things get weirder. Even if the universe is flat locally, it could have a global topology that loops back on itself, like a 3D torus, donut shape. In such a universe, traveling far enough could return you to your starting point, but without any curvature. This is called a multiply-connected universe. Some researchers have searched for repeating patterns in the CMB that could suggest such a topology, like echoes of the same region viewed from different angles, but so far, nothing definitive. Still, the idea fascinates cosmologists. It would mean our infinite-looking universe could actually be finite and looped. Why the shape matters. Understanding the shape of the universe tells us how it began, how it evolves, how it might end. In a flat universe, expansion continues forever, eventually leading to heat death. In a closed universe, a big crunch or big bounce might follow. In an open universe, expansion accelerates endlessly, and galaxies become isolated islands in an ever-darkening sea. The shape also hints at what lies beyond the observable universe. Is space truly infinite? Or are we living in a cosmic hall of mirrors? And perhaps most profoundly, the shape tells us about the initial conditions of the universe and whether our reality was fine-tuned to exist at all. Final thought. We may never see the entire universe, but through careful observation, mathematics, and imagination, we can trace the curvature of reality itself, flat, curved, or twisted into something stranger. Space is not just where things happen. It is what happens. And here on Infinity Beyond, we'll keep following that curve to wherever it leads. We've journeyed through galaxies, black holes, and the shape of the universe itself. But now, we turn inward to a question that may be even more profound than the structure of space-time. Could the universe be conscious? It sounds like philosophy or even science fiction. But this question is increasingly being explored by physicists, neuroscientists, and cosmologists alike. Because when you ask what the universe is made of, atoms, energy, space-time, you must also ask, what is awareness, and where does it come from? Let's unravel the bold, bizarre, and possibly beautiful idea that consciousness and the cosmos may be more intertwined than we ever imagined. The mystery of consciousness. Let's begin with a simple but unsolved problem. What is consciousness? Despite centuries of philosophy and decades of neuroscience, we still don't know exactly how subjective experience, the feeling of being you, arises from physical matter. This is called the hard problem of consciousness. We can explain brain chemistry, neuron signaling, and behavior. But how do electrical signals become thoughts? How do molecules become mind? Some scientists believe that consciousness is an emergent property, something that arises when matter becomes complex enough, like in the human brain. But others believe consciousness may be something deeper, something fundamental to the structure of reality. That's where things get cosmic. Panpsychism, mind everywhere? One of the oldest, and now revived, theories is called panpsychism. It proposes that consciousness is not something brains create, but something that exists everywhere, embedded in all matter, like mass or charge. In this view, atoms have proto-consciousness, not thoughts or feelings, but building blocks of awareness. When arranged in complex systems, this consciousness combines into the rich experience we call the mind. It's like how hydrogen and oxygen combine to create water. Consciousness may emerge when certain conditions are met. If true, this means the universe is not just a collection of stuff, but a field of experience, a cosmic mosaic of awareness. Even stranger, this idea aligns with certain interpretations of quantum mechanics. Quantum consciousness? In quantum physics, particles don't have defined positions until measured. They exist in superpositions, multiple states at once. Only when observed do they collapse into a definite state. Some scientists, like Roger Penrose and Stuart Hameroff, propose that consciousness itself may be linked to quantum processes in the brain. Others flip the idea entirely. Maybe consciousness is what causes collapse, what selects one reality out of many. This leads to the mind-blowing suggestion that awareness is baked into the fabric of quantum reality, and the universe doesn't just allow observers, it may require them. The participatory universe. Physicist John Archibald Wheeler, who worked with Einstein, proposed something even more radical: the participatory anthropic principle. It suggests that observers are not just passive recorders of the universe, they are participants in shaping it. According to Wheeler, the universe doesn't fully exist in its current form until it is observed. This echoes quantum mechanics and raises a deep question. Could the act of observation have helped bring the universe into being? Is consciousness not just a product of the universe, but a partner in its unfolding? The universe as a brain? Let's scale up. Recent studies have shown eerie similarities between the structure of neural networks in the brain and the cosmic web, the vast structure of galaxies, filaments, and voids that make up the universe. When compared mathematically, the connectivity patterns, node densities, and information flow in brain cells and cosmic structures are strikingly similar, despite being separated by 27 orders of magnitude. Some scientists suggest that the universe may process information in a way that resembles a brain. Could it be thinking? We don't mean that the universe has a personality or opinions, but it could be that the universe stores, transmits, and evolves information, and that consciousness is a feature, not a flaw, of this process. Consciousness and the cosmological constant. Now let's get strange. The cosmological constant, the energy density of empty space, is small but not zero. It's responsible for dark energy, which accelerates the universe's expansion. Theoretically, it could have taken on many values, most of which would make life impossible. But we exist in a universe where the constant is finely tuned for conscious observers to emerge. Coincidence or necessity? This observation underlies the anthropic principle, the idea that the universe must have properties that allow observers to exist because we're here to observe it. Some go further and ask, did the universe know we were coming? Simulation and mind. Now recall the simulation hypothesis, segment 8, the idea that we might be living in a computer simulation. If true, then the universe is conscious by design, built by an intelligence to create or explore or simulate reality. But even in a natural universe, consciousness may be inevitable, a law of complexity, a destiny written into atoms. As matter organizes, experience awakens. And what if that's the point? Final thought. Whether you believe consciousness is fundamental or emergent, divine or accidental, one thing is clear: you are the universe made self-aware. Through your eyes, the cosmos sees itself. Through your thoughts, it contemplates its own structure. Through your questions, it continues to evolve. We often look up and ask, what is out there? But maybe we should also ask, what is in here? And recognize they may not be so different after all. Here on Infinity Beyond, we believe the greatest mysteries are the ones that connect mind and matter, soul and star, thought and cosmos, because, in the end, the universe may not just be made of atoms, it may be made of awareness. We've explored black holes, those terrifying cosmic monsters that swallow light, time, and information. But what if the universe contains their mirror opposites? What if, instead of consuming everything, there are objects that only expel matter? These hypothetical entities are known as white holes. And if they exist, they could solve some of the biggest puzzles in astrophysics, or even connect us to parallel universes. Let's dive into one of the most mysterious, least understood, and potentially most important ideas in modern physics: the white hole. What is a white hole? In essence, a white hole is the time reverse of a black hole. Where a black hole pulls matter in and never lets it escape, a white hole ejects matter, but nothing can ever enter it. Imagine a region of space-time where particles and energy come flying out, but where no object, not even light, can cross the boundary inward. It's like a cosmic fountain, spitting material into space, but completely sealed off from incoming matter. It sounds exotic, but mathematically, white holes naturally arise from the equations of general relativity, the same way black holes do. Einstein's field equations don't forbid them. In fact, the original solution to the Schwarzschild metric, the solution that describes a non-rotating black hole, also includes a white hole. But while we've observed dozens of black holes, we've never seen a white hole. So, why not? Why haven't we found one? There are a few reasons why white holes remain elusive. Instability. White holes are thought to be inherently unstable. Any small disturbance, a photon, a bit of dust, could disrupt the conditions needed for a white hole to remain open, possibly causing it to collapse into a black hole or disappear. Short lifespans. If white holes exist, they might last only a tiny fraction of a second, especially in the early universe. That makes them extremely difficult to detect. Rarity. White holes may only occur under extraordinary conditions, such as the end stages of black hole evaporation or in regions of quantum gravity. But the idea hasn't gone away. In fact, it's gaining traction in new and exciting ways. White holes and black holes, two sides of the same coin? Some physicists propose that black holes and white holes may not be separate objects, but connected. According to this theory, a black hole doesn't end in a singularity, but bounces back due to quantum effects, releasing its contents in the form of a white hole. In this model, black holes don't destroy information. They store and later release it, solving the infamous black hole information paradox. This idea is part of a larger framework called loop quantum gravity, an attempt to unify quantum mechanics and general relativity. One proposal by physicist Carlo Rovelli suggests that after a long period, perhaps even longer than the current age of the universe, a black hole could transition into a white hole, spewing out the information it absorbed over time. This would preserve the laws of quantum physics and potentially reveal what lies beyond the event horizon. Could the Big Bang have been a white hole? Here's where things get really interesting. Some scientists believe the entire universe may have emerged from a white hole. In this view, the Big Bang wasn't the beginning of everything from nothing, but rather the explosive emergence of matter from a white hole formed in a parent universe. Essentially, the death of a black hole in one universe becomes the birth of a new one, through a white hole. It's a variation on the cosmic bounce theory, linking black hole collapse to universal creation. If true, it would mean our universe is part of a cosmic family tree, branching endlessly across dimensions and time. White holes and wormholes. White holes also appear in certain wormhole solutions. A wormhole, or Einstein-Rosen bridge, connects two regions of space-time. In this configuration, one mouth of the wormhole is a black hole, the entrance, and the other is a white hole, the exit. This concept inspired decades of science fiction, from Interstellar to Stargate, and raises tantalizing possibilities. Could white holes allow travel between galaxies? Could they provide safe passage through time? Could they serve as cosmic escape routes? Unfortunately, traversable wormholes require exotic matter, with negative energy density, which we haven't yet discovered. But some quantum gravity theories suggest that Planck-scale wormholes may exist, hidden in the foam of space-time. If so, white holes could be embedded throughout the quantum structure of the universe, waiting to be unlocked. Could we detect a white hole? Though no white hole has ever been confirmed, researchers have proposed ways they might reveal themselves. Explosive gamma-ray bursts. Some sudden, short-lived gamma-ray bursts could be caused by microscopic white holes briefly ejecting matter and energy. Unusual gravitational signatures. White holes would affect surrounding space-time, possibly mimicking black holes, but with key differences in motion, light behavior, and radiation. Primordial remnants. White holes may be relics from the early universe, now faded but detectable through patterns in cosmic background radiation or dark matter halos. If any of these signals are found, it would change everything, proving that time-reversed structures exist and that the universe is far stranger than we imagined. Final thought. White holes may remain purely theoretical, for now, but their existence is not forbidden by the laws of physics. They offer a mirror to our understanding of space, time, gravity, and information. And perhaps they hold the key to reconciling quantum mechanics with general relativity. They could be ancient echoes from before time began, or they could be waiting at the end of black holes, holding secrets of other worlds. Here on Infinity Beyond, we believe the universe whispers in opposites, light and dark, matter and antimatter, black holes and white ones, and somewhere in between, the truth awaits. For centuries, astronomy was a visual science. We explored the cosmos by observing light, from the twinkling of stars to the glow of distant galaxies. But in 2015, something changed. For the first time in human history, we heard the universe. It wasn't a sound in the air, but a ripple in the fabric of reality itself, a disturbance in space-time. This was the discovery of gravitational waves, and it marked the beginning of a new era in astrophysics. Let's explore what gravitational waves are, how we detected them, and what they're revealing about the dark, violent symphony of the cosmos. What are gravitational waves? Gravitational waves are ripples in space-time caused by the acceleration of massive objects. Think of space as a flexible sheet. If you drop a bowling ball onto it, it creates a dimple. That's gravity. Now imagine two massive balls orbiting each other. Their motion sends waves rippling across the sheet. These ripples travel outward at the speed of light, stretching and squeezing space itself. Albert Einstein predicted their existence in 1916 as part of his general theory of relativity, but he believed they'd be too faint to ever detect. He underestimated human determination. Where do gravitational waves come from? Only the most extreme events in the universe generate gravitational waves strong enough for us to detect. Merging black holes. Two black holes spiraling into each other generate massive gravitational waves in their final seconds before collision. Neutron star collisions. When two neutron stars merge, they emit gravitational waves, and often light, gamma rays, and heavy elements like gold. Supernovae. The explosive death of a massive star can send shockwaves through space-time. The early universe. Some theories predict that primordial gravitational waves were created just after the Big Bang, echoing across space-time. These cosmic events are among the most energetic and mysterious phenomena known, and gravitational waves let us hear them across the void. How do we detect them? Gravitational waves stretch and compress space by less than the width of a proton. To detect something so small, scientists built one of the most precise instruments ever made: LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO has 2 arms, each 4 kilometers long. A laser beam is split and sent down each arm. If a gravitational wave passes through Earth, it slightly changes the length of one arm compared to the other, producing an interference pattern in the laser. It's like detecting a change the size of an atom over 4 kilometers. The first detection came on September 14, 2015. A faint, rising chirp. It was the death cry of 2 black holes merging 1.3 billion light-years away. Since then, LIGO and its European partner Virgo have detected dozens of gravitational wave events, and the list is growing. Why gravitational waves matter. This is more than just a new way of observing space. Gravitational waves are a revolution. They allow us to see the invisible. Black holes don't emit light, but when they merge, they scream in gravitational waves. Test relativity. Every wave we detect confirms or challenges Einstein's predictions. Measure cosmic distances. Like cosmic sonar, gravitational waves help us map space. Study extreme matter. Neutron stars are the densest matter in the universe. Their collisions teach us about physics beyond Earth. Explore cosmic origins. Primordial waves could reveal secrets about the Big Bang, inflation, and quantum gravity. It's like discovering a whole new sense. For the first time, we're not just seeing the universe. We're listening to it. The music of the cosmos. Gravitational waves don't produce sound in space, but when converted into audio frequencies, they can be heard. And they sound astonishing. The first signal, GW15914, resembled a chirping bird, rising in pitch and frequency until it suddenly stopped. That was the moment 2 black holes collided. Other detections sound like drum beats, hums, or ringing tones, depending on the mass, spin, and speed of the merging objects. Each waveform is unique, a signature of a cosmic event billions of years ago. It's like discovering the soundtrack of the universe. Multi-messenger astronomy. One of the most groundbreaking detections came in 2017. A neutron star merger called GW170817. For the first time, gravitational waves and light were detected from the same event. Astronomers observed gravitational waves, gamma rays, optical light, X-rays, and even radio waves, all from a single cosmic collision. This ushered in multi-messenger astronomy, where we observe the universe with multiple signals, not just light. It's as if the universe went from silent film to full surround sound. The future of gravitational wave astronomy. We're just getting started. Future detectors will take us even deeper. LISA, the Laser Interferometer Space Antenna, will launch in the 2030s. It will detect lower frequency waves from supermassive black hole mergers across the universe. Einstein Telescope, a proposed underground European detector with 10x the sensitivity of LIGO. Cosmic Explorer, a next-generation U.S. observatory to probe early universe signals. We may even detect primordial gravitational waves, the faint echoes of the Big Bang itself. And with more data, we could discover new physics, extra dimensions, exotic particles, or changes in gravity over time. Final thought, gravitational waves have opened a new sense, a way to hear the deepest movements of the universe. They come from cataclysms, collisions, and creation itself, and they carry messages that light can't deliver. In every ripple, we find not just evidence of the past, but proof that the universe is alive with motion, drama, and music. Here on Infinity Beyond, we listen closely, because the universe is speaking, and its voice is beautiful. We gaze into the night sky and see billions of stars. Many of those stars have planets, and many of those planets, we now know, lie in the habitable zone, not too hot, not too cold, where life could flourish. The ingredients for life, carbon, water, energy, are everywhere in the cosmos. So here's the big question. If life is so common, where is everybody? This question is known as the Fermi paradox, and it's one of the greatest unsolved mysteries in science. Let's dive deep into this cosmic riddle, the theories, the possibilities, and the unsettling answers that may lie just beyond our reach. The origins of the paradox. The paradox is named after physicist Enrico Fermi, who, during a lunchtime conversation in 1950, reportedly asked, "But where is everybody?" At the time, radio and nuclear technologies were advancing quickly. If intelligent civilizations existed, and if they were even slightly ahead of us, they should have spread across the galaxy, or at least left behind signs. The paradox is this. The Milky Way is over 13 billion years old. There are more than 100 billion stars, many older than our Sun. With modest technology, a civilization could colonize the galaxy in just a few million years. But we see no evidence, no alien probes, no radio signals, no Dyson spheres, nothing. It's eerily quiet out there. Possibility number 1, where early one explanation is that we're among the first intelligent civilizations. Perhaps life is common, but intelligence is rare, or takes a very long time to evolve. If that's true, then we're not late to the party. We're setting the table. We might be among the first sparks of cosmic consciousness. But this raises new questions. Why now? Why us? Is there something special or dangerous about reaching this stage of evolution? Possibility number 2, they're too far away. The universe is vast, and expansion makes it even bigger. Perhaps alien civilizations are too far to detect. Their signals might not have reached us yet, or they're using technologies beyond our comprehension. Maybe we're like ants, unaware of the freeway nearby, simply not listening the right way. Or maybe signals degrade, or civilizations are speaking in non-electromagnetic ways, through neutrinos, quantum entanglement, or something entirely unknown. We could be surrounded by messages and not even know how to look. Possibility number 3, they don't want to talk. This is known as the zoo hypothesis. It suggests that advanced civilizations know we're here, but are deliberately avoiding contact. They may be observing us silently like scientists studying wildlife. They might believe in non-interference or think we're not ready. Imagine Earth as a galactic preserve, quarantined for its own safety, or theirs. Alternatively, contact may be forbidden by a universal law or culture we don't understand. If this is true, the silence is intentional. Possibility number 4, they destroy themselves. This is perhaps the most chilling answer. Maybe civilizations do emerge, but don't last. Advanced technology comes with existential risk. Nuclear weapons, climate collapse, AI, pandemics. These are hurdles we're already facing. What if the development of powerful tech is almost always followed by self-destruction? This theory suggests a great filter, a stage in evolution that most civilizations don't pass. We might be approaching it, or maybe we already passed it, and that's why we're still here. Either way, the silence could be the echo of extinction. Possibility number 5, they're already here. Some theorists suggest that aliens have visited Earth, or are still here, but remain hidden. They may operate at microscopic scales, hide in higher dimensions, or disguise themselves within nature. Ancient astronaut theories, UFO sightings, and mysterious artifacts have fueled speculation, but no definitive proof exists. Still, the possibility that aliens walk among us, unnoticed or undetectable, is both thrilling and terrifying. If true, it changes everything. Possibility number 6, we're in a simulation. What if we're not in the real universe at all? The simulation hypothesis suggests that we live in a virtual reality, perhaps created by an advanced intelligence. In this framework, the universe is designed, and the absence of aliens might be a programmed limit to reduce complexity or preserve narrative. Maybe we're the focus of this simulation, or maybe we're just a subroutine, a side project in a much larger simulation. Either way, the silence may not be natural, but intentional design. The Drake equation. To estimate the number of intelligent civilizations, astronomer Frank Drake created the Drake equation in 1961. It includes factors like the number of stars formed per year, the fraction with planets, the number of habitable worlds, the likelihood of life, intelligence, and communication. The lifespan of civilizations. Depending on your assumptions, the equation gives numbers ranging from 0 to millions. But here's the catch. Many of these factors are still unknown. The Drake equation is less a calculation and more a framework for wonder. Final thought. The Fermi paradox remains unresolved. But maybe that's the point. Maybe the silence isn't a warning, but an invitation to listen harder, to search further, to reflect more deeply on what it means to be intelligent, alive, and alone in the cosmos. Whether we're the first, the last, or somewhere in between, our responsibility is the same: to explore, to survive, to become the kind of civilization that others would be glad to find. Here on Infinity Beyond, we'll keep asking, not just where is everybody, but who are we becoming? If aliens exist, how advanced could they be? Would they have flying saucers and laser weapons? Or would they be so far beyond us that we'd mistake their technology for the laws of nature? To help frame this possibility, astrophysicist Nikolai Kardashev proposed something revolutionary in 1964, a way to classify civilizations based on the energy they can harness. This became known as the Kardashev scale, a cosmic ladder from primitive life to godlike empires. Let's explore what it means, where we are on it, and how it reshapes our understanding of the future and the galaxy. The Kardashev scale. An overview. The scale has 3 main levels. Type 1, civilization, harnesses all the energy available on its home planet. Think, controlling weather, oceans, volcanoes, mastering planetary systems. Type 2 civilization utilizes the total energy output of its home star. Think, building a Dyson sphere around the sun to capture every photon of light. Type 3 civilization controls the energy of an entire galaxy. Think, manipulating star systems, harnessing black holes, perhaps even reshaping galactic arms. It's a scale not of culture, ethics, or intelligence, but raw power. And it tells us how far a civilization can expand its reach into the cosmos. Where are we? Right now, humanity is not even on the scale. According to updated estimates, we are around type 0.73. We still burn fossil fuels. We rely on inefficient energy grids. We haven't colonized the oceans, let alone the solar system. But we're advancing quickly. With sustainable fusion energy, space colonization, AI-managed infrastructure, and climate control, we could reach Type 1 in a few hundred years. Becoming a Type 1 civilization would mark humanity's transition from a fragile species to a planetary power. But the real challenge and wonder lies beyond. Type 2 civilizations, masters of the stars. A Type 2 civilization would no longer be bound to its planet. It would harvest the energy of its host star and possibly others using massive engineering projects like Dyson spheres or Dyson swarms. These structures would surround a star and collect nearly all of its energy output. With that power, they could terraform planets, move moons into habitable orbits, power megastructures the size of worlds, launch interstellar missions at massive scale. The energy output of a single star dwarfs anything Earth has ever produced. To harness it would be to ascend into a truly cosmic species. But how would we detect such a civilization? Searching for Type 2 civilizations. We may not be able to contact such advanced beings, but we might see their footprints. A Dyson sphere, for example, would block visible light but radiate infrared heat. We could look for stars with strange thermal signatures, glowing but oddly dim. In 2015, astronomers found a candidate, KIC 8462852, also known as Tabby's star. It dimmed irregularly, unlike any known star. Some speculated it could be a Dyson swarm. Later analysis pointed to dust or comets, but the mystery remains open. We've also looked for waste heat across galaxies, entire regions with missing starlight or anomalous radiation. So far, no conclusive evidence, but the search is only beginning. Type 3 civilizations, galactic engineers. Now imagine a civilization that doesn't just manipulate stars, but entire galaxies. A Type 3 civilization would control the energy of billions of stars, black holes, and interstellar gas clouds. Such beings might rearrange star systems, create artificial wormholes, convert matter directly into energy, upload consciousness into cosmic-scale networks. They could appear as godlike forces, altering gravity, space, and even time. Would we recognize them? Or would their activities seem like natural phenomena? In fact, some astronomers believe that Type 3 civilizations may be indistinguishable from astrophysical processes because their technology operates on such a vast and subtle scale. Going beyond, Type 4 and Type 5, though not part of the original Kardashev scale, some theorists speculate about even higher types. Type 4 controls the energy of the entire universe. Type 5 masters the multiverse, if such a thing exists. At these levels, civilizations might manipulate the fundamental constants of physics, create baby universes, or travel through higher dimensions. Of course, this is pure speculation, but it's a useful mental framework for stretching our imagination about what's possible. The Great Filter and the Scale. Now here's a sobering thought. If the Kardashev scale represents a path toward godlike power, then why don't we see evidence of civilizations further along? This ties back to the Fermi paradox, the silence of the stars. One possibility is that few civilizations ever reach Type 1 or 2. They might destroy themselves first, through war, resource exhaustion, or runaway AI. This hypothetical barrier is called the Great Filter. If it lies ahead of us, we may never reach the next rung. If we've already passed it, then we are rare, maybe even unique. Either way, the Kardashev scale is more than science fiction. It's a mirror, reflecting both our potential and our fragility. Final thought. The Kardashev scale isn't just a way to rank alien civilizations. It's a map of humanity's possible futures. From campfires to quantum computers, from planetary engines to stellar megastructures, the journey up the scale is the story of intelligent life pushing the boundaries of nature. Here on Infinity Beyond, we believe that scale isn't just about energy. It's about vision and the courage to dream not just bigger, but wider. Because the universe is vast, and we're just getting started. It feels steady, linear, predictable. 1 second always follows another. But in the vast and warped landscape of the cosmos, time behaves very differently. Welcome to the strange world of time dilation, a phenomenon where time doesn't tick at the same rate for everyone. It stretches, bends, and even slows down, depending on how fast you're moving or how close you are to gravity. Time dilation isn't just science fiction. It's real physics. It's been measured, observed, and confirmed. And if you want to understand black holes, space travel, or even your GPS, you need to understand how time bends. Time isn't absolute. In the early 20th century, our understanding of time underwent a revolution. Albert Einstein's theory of special relativity introduced a stunning idea. Time is relative. According to Einstein, the faster you move through space, the slower you move through time, from the perspective of a stationary observer. In other words, if you're traveling at near the speed of light, your time slows down compared to someone who's standing still. This isn't a metaphor, it's measurable. This effect is known as kinematic time dilation, and it's been proven by countless experiments. The twin paradox. One of the most famous examples of time dilation is the twin paradox. Imagine two identical twins. One stays on Earth. The other boards a spaceship and travels near the speed of light for a few years, then returns. Due to time dilation, the spacefaring twin would have aged less than the one who stayed behind. Maybe by just a few months, or maybe by decades, depending on the speed. This isn't just theoretical. In fact, we've measured time dilation using high-speed jets and incredibly accurate atomic clocks. Astronauts aboard the International Space Station actually age slightly slower than people on Earth, though by fractions of a second. Gravity slows time. Einstein didn't stop at special relativity. He went further, developing general relativity, which describes how gravity warps time. According to this theory, the stronger the gravitational field, the slower time passes. This is called gravitational time dilation. Near a massive object, like a black hole, time ticks more slowly compared to areas with weaker gravity. If you stood on the edge of a black hole just outside the event horizon, an hour might pass for you, while years pass for someone far away. This isn't science fiction, it's the very idea behind Interstellar, and it's backed by solid physics. Real-life time dilation. You may not feel it, but time dilation affects your daily life. Your smartphone's GPS uses satellites orbiting Earth. Those satellites experience both types of time dilation. They move faster than we do, which makes their clocks tick slower. But they're further from Earth's gravity, which makes their clocks tick faster. To work properly, the system has to correct for both effects. If not, your GPS could be off by kilometers every day. So every time you get directions, you're using Einstein's theories. Time dilation, near a black hole. Let's revisit black holes, the ultimate playground of warped time. The gravitational pull of a black hole is so strong that time near its edge practically stops from the viewpoint of a distant observer. This means that theoretically, you could use a black hole to time travel into the future. Spend a few minutes near its event horizon, and decades might pass in the universe outside. This is one of the most extreme examples of gravitational time dilation, and it's why black holes are such powerful thought experiments in relativity. Fast-forwarding to the future. Here's something fascinating. Time dilation is one-way time travel. You can't go back, but you can jump forward by slowing your own clock. If a spacecraft could approach 99.999 the speed of light, astronauts aboard could experience weeks, while years pass on Earth. This idea is central to many sci-fi concepts, like the time traveler who returns home to find centuries have passed. While we can't yet reach such speeds, time dilation tells us the future is accessible if we can move fast enough or harness powerful gravity. Implications for interstellar travel. Why does this matter? Because time dilation could be a tool for space exploration. If future humans travel on relativistic starships, they could reach nearby stars in a single lifetime, from their perspective. Meanwhile, Earth would age much faster. A journey to Proxima Centauri might take 4 years from our viewpoint, but mere months on board a high-speed vessel. The cost, of course, is the loss of synchrony. You'd return to find your homeworld much older, or unrecognizable. Still, it opens up the possibility of practical interstellar missions. Philosophical perspective. Time dilation forces us to rethink the nature of time itself. It isn't a universal clock ticking in the background. Time is local, flexible, and shaped by motion and gravity. In the grand cosmic dance, every object experiences time in its own unique way, creating a tapestry of personal timelines across the universe. The passage of time, it turns out, is one of the most personal experiences in physics. And in a strange, poetic way, relativity reminds us. We all live in different moments. Final thought. Time dilation isn't just a curiosity. It's a profound reality woven into the structure of the universe. It bends our understanding of motion, gravity, and experience itself. It's the reason black holes freeze time, the reason GPS works, the reason time travelers may someday leap forward. And it's a reminder that time, like space, is not fixed, but a dimension we're only beginning to explore. Here on Infinity Beyond, we're not just watching the clock. We're watching how the clock changes. Because in a universe where time bends, the future belongs to those bold enough to chase it. What if our universe is not the only one? What if everything we know, stars, galaxies, even the laws of physics, are just a tiny bubble in an unimaginably vast cosmic ocean? This is the core idea behind the multiverse theory, a concept that challenges our deepest assumptions about reality. Far from being pure science fiction, the idea of a multiverse is being taken seriously by physicists, cosmologists, and philosophers alike. In this episode of Infinity Beyond, we dive into the wild world of parallel universes, exploring the science, the speculation, and the staggering implications of infinite realities. What is the multiverse? The word multiverse refers to the hypothetical existence of multiple, possibly infinite, universes. Each of these universes may have its own laws of physics, dimensions, particles, and constants, and may be completely separate from our own. Some may be eerily similar, differing only in the outcome of a single event. Others could be so foreign that time, matter, and logic behave in ways we can't even imagine. In essence, the multiverse theory suggests that our universe is just one of many, perhaps one of infinitely many. Level 1. Infinite universe. The simplest form of multiverse starts right within our own Big Bang model. If the universe is infinite and space continues forever, then somewhere out there, far beyond the observable universe, there could be regions with identical copies of you. This idea comes from basic probability. In an infinite space, with a finite number of particles and possible configurations, repetition is inevitable. So, somewhere out there is a version of you watching this video, but wearing a red shirt instead of blue. And another version where Earth never formed, or where dinosaurs never went extinct. This is known as the Level 1 multiverse, infinite space, infinite possibilities. Level 2. Bubble universes. According to inflationary theory, shortly after the Big Bang, space underwent a rapid expansion, faster than the speed of light. Some versions of inflation suggest that this expansion never fully stopped. Instead, it continues in most regions, occasionally creating bubbles that stop inflating and form individual universes, like ours. Each bubble is a separate universe with its own physical constants. This leads to the Level 2 multiverse, where universes form like bubbles in a cosmic foam, each with different laws of physics. Our universe might be just one bubble in a vast foaming multiverse. Level 3. The Many Worlds Interpretation. Now we enter the quantum realm. The Many Worlds interpretation of quantum mechanics suggests that every quantum event, every time a particle has multiple possible outcomes, all of them actually happen. but in separate branches of reality. This means that with every decision, every roll of the dice, every fluctuation, the universe splits into parallel worlds. This is the Level 3 multiverse, where an infinite number of yous live out every possible outcome of every choice you've ever made. In one world, you became a scientist. In another, an artist. In yet another, you never existed at all. It's a multiverse branching from your own life, constantly. Level 4, Mathematical Universes. The most abstract version is the Level 4 multiverse, proposed by physicist Max Tegmark. This theory suggests that all mathematically possible universes exist, not just variations of physics, but variations of logic, structure, and reality itself. In this model, the universe isn't made of matter, but of math. Every consistent mathematical structure corresponds to a universe. Some may resemble ours. Others may be completely unrecognizable. This is the most expansive and controversial version of the multiverse, but it also reflects a deep question. Is math invented by humans or discovered because it's the fabric of reality, evidence, and challenges? Here's the tricky part. We can't currently observe other universes. By definition, they're beyond our observable horizon, or completely disconnected from our space-time fabric. Still, several pieces of indirect evidence keep the multiverse hypothesis alive. Cosmic microwave background. Tiny anomalies might hint at collisions with other bubble universes. Fine-tuning. Our universe's physical constants are precisely calibrated for life. A multiverse provides a natural explanation. We exist in a universe where conditions allow observers to exist. Mathematical elegance. Some models of physics, like string theory, predict a multiverse naturally. But the main criticism is falsifiability. If we can't test it, is it science? Some argue that without direct evidence, the multiverse remains philosophy, not physics. Philosophical implications. If the multiverse is real, it changes everything. It challenges the uniqueness of our universe, our planet, even ourselves. It means that every possibility is played out somewhere. Every version of history, every alternate timeline, they all exist, with their own observers, stars, and questions. It also raises ethical and existential questions. If every choice creates a new universe, does free will exist? If every tragedy happens somewhere, how do we find meaning? If nothing is truly unique, what matters most? The multiverse forces us to look beyond the visible and confront the infinite. Final thought. Whether it's a cosmic foam of universes, infinite quantum branches, or math-born realities, the multiverse idea is more than just a wild theory. It's a mirror of imagination and a test of humility. Because if our universe is just one of countless others, then the cosmos is far stranger and far grander than we ever imagined. Here on Infinity Beyond, we're not just peering into the stars, we're peering into every possible version of them. And the only question left is, which universe are you in right now? We've all heard of black holes, terrifying objects in space that devour everything, even light, never letting anything escape. But what if there was a cosmic mirror to the black hole, an object that does the exact opposite? Instead of sucking matter in, it expels it. Instead of hiding information, it throws it out. A place where nothing can enter, but everything pours out. These theoretical objects are called white holes, and they may be one of the weirdest and most fascinating possibilities in modern astrophysics. In this episode of Infinity Beyond, we're diving into the explosive, mysterious, and potentially real world of white holes, the cosmic opposites of black holes. What is a white hole? A white hole is a hypothetical region of space-time that acts as a reverse black hole. A black hole pulls everything in and lets nothing escape. A white hole expels matter and light, and nothing can go in. Imagine a cosmic fountain, endlessly spewing out radiation and matter, but completely impenetrable from the outside. White holes violate time symmetry in the opposite way black holes do. If you reverse the flow of time through a black hole's equations, you get a white hole. They're not just science fiction. White holes are a mathematical solution to Einstein's equations of general relativity. But do they exist in the real universe? That's where things get weird. A mathematical mirror. Black holes and white holes are connected through what's known as a maximally extended solution to the Schwarzschild metric, a mathematical description of space-time around a massive, non-rotating body. In this solution, a black hole is linked to a white hole through a wormhole, a theoretical bridge connecting two regions of space-time. This bridge is sometimes referred to as an Einstein-Rosen bridge. In theory, an object falling into a black hole could emerge from a white hole somewhere else in the universe, or in another universe entirely. But there's a problem. These bridges seem to be unstable. They collapse too quickly for anything to pass through. Still, they offer an astonishing picture. Black holes as cosmic drains, white holes as cosmic springs. Are white holes real? So far, no white holes have ever been observed. They remain a speculative concept, a consequence of mathematical symmetry, not physical evidence. But some physicists suggest that white holes could explain certain cosmic phenomena. For example, some gamma-ray bursts, powerful explosions from deep space, might be the result of short-lived white holes expelling energy. White holes might be connected to dark matter, the mysterious invisible substance that permeates the universe. They could be remnants of dying black holes, transforming at the end of their lives into white holes that release their contents. The idea of black holes turning into white holes is especially intriguing because it could solve one of physics' most pressing mysteries. The information paradox. Black holes raise a disturbing problem in quantum physics. When something falls in, its information seems to be lost forever. This violates a fundamental principle of quantum mechanics. Information must be conserved. So what happens to the information swallowed by a black hole? Some physicists, including Stephen Hawking, have suggested that black holes might not erase information after all. Instead, they may eventually release it back, somehow. One radical idea. At the very end of its life, after evaporating via Hawking radiation, a black hole bounces into a white hole, expelling all the trapped information. This leads to a beautiful possibility, that white holes are the final act of black holes. They could be the key to reconciling gravity and quantum mechanics. Loop quantum gravity and white holes. One of the theories exploring this transformation is loop quantum gravity, an alternative to string theory. According to this idea, space-time is not smooth and continuous, but quantized, made up of tiny loops of energy. In this framework, the collapse of a black hole doesn't lead to a singularity. Instead, it reaches a minimum size and rebounds, forming a white hole. This process could happen very quickly from the black hole's point of view, but appear to take billions of years to an outside observer. If true, white holes might be all around us, hiding inside the remnants of dead stars, waiting for their moment to burst open. Could the Big Bang have been a white hole? Here's a truly mind-blowing idea. What if our entire universe emerged from a white hole? The Big Bang looks suspiciously like a white hole event, a sudden, massive expansion of energy and matter from a single point. Some theorists suggest that our universe might be the interior of a white hole formed from the collapse of a star in another universe. This is speculative, but deeply compelling. It would mean we live inside a white hole, born from another reality, part of an eternal cycle of cosmic births and deaths. Philosophical implications. If white holes exist, They force us to rethink the nature of space, time, and information. They may represent the arrow of time, pointing outward, dispersing, expanding, rather than collapsing inward. They may be evidence of mirror realities, universes that are time-reversed reflections of our own. Or they may simply be reminders that our understanding of physics is still incomplete. In a cosmos filled with mysteries, white holes stand as one of the boldest and least understood. Final thought. White holes are strange. They're unpredictable, untouchable. They spit out matter, reject entry, and defy easy explanation. But they also represent a beautiful symmetry, the idea that for every sink, there might be a spring. For every collapse, an explosion. For every end, a beginning. Whether real or theoretical, white holes push the boundaries of what we consider possible. And here on Infinity Beyond, that's exactly where we like to be. Everything has a beginning and an end. Stars are born, burn brightly, then fade. Galaxies form, swirl with life, and slowly drift apart. Even the universe itself had a fiery birth, the Big Bang. But what happens at the end of time? How does the cosmos die? In this episode of Infinity Beyond, we journey to the deep future of the universe. Trillions upon trillions of years ahead to explore a chilling possibility. The heat death. It's not a fiery explosion or a dramatic collapse. It's something far more haunting, a slow, silent fade into nothingness. Entropy, the universe's final countdown. To understand the heat death, we must first grasp a fundamental law of physics, the second law of thermodynamics. It states that entropy, a measure of disorder, always increases over time in a closed system. In simple terms, the universe is constantly moving from order to chaos, from structure to randomness, from energy to equilibrium. This trend is irreversible, and when entropy reaches its maximum, everything stops. That's heat death, the moment when no more work can be done because everything is evenly spread out. No stars, no galaxies, no life, just cold, quiet emptiness. Timeline of cosmic decay. Let's walk through the stages of cosmic demise. 1. Present day to 109 years. Stars continue to shine. Galaxies evolve. Life, at least in some corners, may still exist. 2. 10 on 14 on 10-15 years. Degenerate era. Most stars burn out. What remains are white dwarfs, neutron stars, and black holes. The universe is dark. Stellar remnants drift silently. 3. 1030-1040 years. Black hole era. Even black holes start to vanish, slowly radiating away via Hawking radiation. Eventually, only subatomic particles remain. 4. 100 years and beyond. Heat death. Entropy reaches its peak. All usable energy is gone. No more stars, no more movement. The universe becomes a cold, featureless void. This is not a violent death, it's the fading of the cosmic flame. Why heat death? The term might sound contradictory. Shouldn't death mean cold? Yes, but the name comes from thermodynamics, not temperature. Heat death means the complete spread of thermal energy throughout the universe, to the point where there are no energy gradients left. Without differences in energy, no engines run, no reactions spark, and no life can survive. It's like a battery drained to zero, permanently. Will black holes outlast everything? For a long time, it was thought that black holes were eternal, but Stephen Hawking changed that. He proposed that black holes slowly emit radiation, now called Hawking radiation, and eventually evaporate over unimaginable timescales. A supermassive black hole may take up to 100 years to vanish. After that, nothing with mass remains, only ghostly radiation, in a cold, expanding void. Quantum possibilities. Could something survive? Some physicists suggest that quantum fluctuations, brief, random appearances of particles, could continue to occur even after heat death. This leads to wild theories. Boltzmann brains, random brains forming in the void with fleeting moments of consciousness. Vacuum decay, a sudden catastrophic shift in the laws of physics that erases the universe entirely. Quantum rebirth, new universes bubbling up from the quantum foam. These are speculative, but they show that even in the stillness of heat death, physics may still whisper. Philosophical reflections. The idea of heat death is unsettling. It paints a future with no escape, no heroes, and no second chances. But it also invites reflection. We are alive during the bright age of the cosmos. Stars still shine. Life thrives. Thought exists. We are part of a fleeting miracle, a moment of structure in a sea of entropy. Heat death reminds us that time is precious, that the universe isn't eternal, that our brief moment in the light should be lived fully. Alternate fates of the universe. While heat death is the most widely accepted theory, it's not the only one. Other models include Big Crunch. The universe collapses back on itself. Big Rip. Dark energy accelerates expansion until everything is torn apart. Big Bounce. A cycle of expansion and collapse, repeating endlessly. But current observations, especially the universe's accelerating expansion, support the heat death scenario most strongly. It's a slow goodbye, not a bang, but a sigh. Final thought. The heat death isn't about destruction. It's about stillness. No explosions, no fires, just silence, cold, and a slow dimming of everything we know. And yet from this knowledge comes clarity. Life is not permanent, but it is precious. Stars don't burn forever, but while they do, they shine for us. Here on Infinity Beyond, we look into the darkness, not with fear, but with wonder. Because even as the universe winds down, the story it tells is one of magnificent beginnings, breathtaking beauty, and the brief miracle of consciousness. In the face of heat death, we are the spark. The universe is expanding. We've known that for nearly a century. Galaxies are racing away from one another as space itself stretches in all directions. But what if something strange is pulling parts of our universe in one specific direction? Not just drifting, not just expanding, accelerating towards something vast, invisible, and unknown. Welcome to the mystery of the dark flow, one of the most puzzling and controversial observations in cosmology. In this episode of Infinity Beyond, we explore a cosmic anomaly that defies our models and hints at something beyond the edge of the visible universe. The cosmic microwave background, our map of the early universe. In 1965, scientists discovered the cosmic microwave background, CMB, the faint afterglow of the Big Bang still echoing through space. This ancient light is remarkably uniform, but it contains subtle fluctuations, tiny temperature differences that reveal how matter was distributed in the early universe. Think of the CMB as a cosmic baby picture, showing us what the universe looked like just 380,000 years after it began. We use it to study the shape, composition, and motion of everything in the cosmos. But in 2008, a strange asymmetry appeared in the data, something that couldn't be explained by ordinary expansion. It looked like hundreds of galaxy clusters were all moving in the same direction, and they were moving fast. What is dark flow? Dark flow is the name given to this mysterious motion of galaxy clusters toward a specific region of the sky. Measurements from NASA's WMAP and later the Planck spacecraft showed that these clusters were moving at over 1,000 kilometers per second, and in a coherent direction. This isn't ordinary cosmic expansion, which is uniform in all directions. This is a drift, like a current in the fabric of space, pulling matter towards some unseen attractor. The cause? Unknown. Some scientists believe this could be a false signal or an artifact of how the data is analyzed. But others suggest something more profound, that the universe we observe is only a small part of a much larger structure, and something outside our cosmic horizon is tugging on us. What could be pulling us? If the dark flow is real, it suggests the influence of something beyond the observable universe. Here are some leading ideas. A giant supervoid or supercluster. An extremely massive structure, far bigger than anything we've seen, could be exerting gravitational pull from beyond our sight. A remnant of the pre-Big Bang cosmos. If the Big Bang was not the beginning, but a transition, there might be remnants of a previous universe affecting ours. A parallel universe. Some multiverse theories propose that other universes exist near ours, separated by a thin boundary. One of these might be gravitationally interacting with our own. Anisotropies in the geometry of space, as space-time itself might not be perfectly smooth or uniform. Large-scale warps could produce directional flows of matter. These ideas are speculative, but they arise from trying to explain what we see in the data. Challenges and controversy. The dark flow hypothesis is highly controversial. Some scientists argue that the data from the WMAP and Planck missions is inconclusive, or that the signal might be statistical noise. Others have failed to replicate the findings with different methods. The debate continues, but what makes the dark flow so compelling is this. Even if the signal is weak, its implications are massive. If confirmed, it would mean that the universe isn't isotropic, that there's a preferred direction in space, and that would shake the foundations of modern cosmology. Observable universe versus actual universe. Let's remember, the observable universe is limited by the speed of light and the age of the cosmos. We can only see objects whose light has had time to reach us, about 46 billion light-years in any direction. But beyond that, the universe may continue indefinitely, and anything beyond our horizon is invisible to us, unless it exerts a force we can detect. The dark flow might be our first clue that the universe is part of something far bigger. What if it's true? If dark flow is real, we'd be facing a cosmic current, one that originates from outside our known universe. That would mean the Big Bang wasn't a local event, but part of a larger cosmic landscape. It could mean the existence of structures bigger than the observable universe, evidence of multiversal interaction, or even a violation of cosmic uniformity, something we've assumed for decades. In other words, dark flow could be a cosmic fingerprint from beyond the veil. What comes next? Future missions, with more sensitive instruments, may help confirm or disprove the existence of dark flow. Projects like CMBS-4 or the Simons Observatory aim to map the microwave background with unprecedented precision. We may discover that dark flow was a mirage, a statistical anomaly. Or we may open the door to a new chapter in cosmology, one where the universe isn't a lonely island, but one of many in a vast cosmic ocean. Final thought. The dark flow is more than just a direction. It's a mystery that points beyond what we can see. It challenges our assumptions. It invites us to think bigger, to consider that the universe we know is just a glimpse of something greater. Here on Infinity Beyond, we follow those currents, not just where they lead, but to what they represent. Because in the tug of the unknown, we find the pulse of discovery. And maybe, just maybe, something out there is calling us. Reality feels solid. The ground beneath your feet, the warmth of the sun, the thoughts in your head. But what if it's all a simulation? What if everything you know, your memories, your senses, your world, is just part of an intricate digital reality created by an advanced intelligence? It's not just a plot from sci-fi films like The Matrix. It's a question that leading physicists, philosophers, and technologists are beginning to take seriously. In this episode of Infinity Beyond, we ask the ultimate question: are we living inside a simulation? The simulation hypothesis. This provocative idea was popularized by philosopher Nick Bostrom in 2003. He proposed a trilemma, a logical argument with three possibilities. Advanced civilizations never reach a technological level capable of running realistic simulations of conscious beings. Advanced civilizations can create such simulations, but choose not to. We are almost certainly living in a simulation. If you assume it's possible to simulate consciousness, and that civilizations would run many such simulations, then the simulated beings would vastly outnumber biological ones. Statistically, that means it's more likely you are simulated than real. It's a logic bomb that shakes the very notion of existence. What would a simulation look like? If we are in a simulation, it would likely have rules, like the laws of physics, coded into its structure. Resolution limits. Just like how video games have render distances, our universe might have quantized pixels of space and time. Processing power constraints, perhaps explaining quantum uncertainty and probabilistic behavior. Think about it. Why does the universe appear mathematically perfect? Why is so much of reality describable by equations? It could be code running on a cosmic computer. Are there clues? Some theorists and scientists have suggested potential glitches or signs in the universe that could hint at its artificial nature. Planck units, the smallest possible divisions of space and time, might be like the pixels of our universe. The speed of light has a cosmic speed limit, like the refresh rate of a processor. Quantum indeterminacy. Particles don't take on properties until observed. Could this be the universe rendering only when needed? Simulation artifacts, like unexpected cosmic rays or anomalies in quantum experiments. These are subtle and highly debatable, but to some, they smell like debugging breadcrumbs. What about consciousness? One of the greatest mysteries in science is consciousness. Where does it come from? How does matter produce awareness? In a simulated universe, consciousness might be an emergent behavior, a byproduct of sophisticated code running in neural networks. But others suggest that consciousness is non-local, not dependent on matter, and possibly even the core program of the simulation itself. This flips the narrative. Perhaps the simulation isn't about physics, but about experience. Perhaps we are being simulated not to model matter, but to explore meaning. Who's running it? If this is a simulation, someone or something must have created it. But who? Future humans, running ancestor simulations to study history, post-biological AI, advanced artificial intelligences exploring consciousness, alien civilizations, far older and more powerful than we can imagine. Unknown creators, outside of space and time, like gods or interdimensional minds. The motives are equally mysterious: science, art, entertainment, punishment, or training. We could be in a lab, a museum, a zoo, or even a video game. The limits of detection. One of the most haunting parts of the simulation hypothesis is this: if it's true, we may never know. The simulation could be designed to hide its tracks perfectly. Any test we devise might be part of the simulation itself. If the creators don't want us to know, we won't. But if the simulation is imperfect, clues may leak through. Strange coincidences, unexplainable phenomena, or moments of déjà vu. And if we ever create simulations of our own, ones as complex as reality, it could be indirect proof that we are inside one too. What if we are? Let's assume for a moment that we are simulated. What does that mean? It doesn't make your life less real. Your thoughts, relationships, pain, and joy still matter. You are still a conscious being, having a valid experience. But it does shift perspective. It suggests that reality is not fundamental, that matter is made of information. It means that meaning and perception might be more real than atoms. And it opens the door to questions about ethics, purpose, and freedom. Spiritual overlaps. The simulation theory echoes ancient spiritual ideas. Hinduism teaches that the world is Maya, an illusion. Plato's cave describes people mistaking shadows for reality. Buddhism suggests that the self is an illusion, and reality is transient. Even Christianity speaks of a creator beyond the physical realm. Maybe science and spirituality are circling the same truth, from different angles. Final thought: are we living in a simulation? Maybe, maybe not. But the question forces us to rethink reality, identity, and existence itself. Whether the universe is made of atoms or bits, what matters is that we are here, questioning, feeling, seeking. On Infinity Beyond, we don't just explore space and time, we explore the nature of reality, wherever it may lead. So if you're part of a simulation, make it a meaningful one. On a clear night, look up. The sky sparkles with stars, hundreds, thousands, each one a sun, many with planets of their own. In just our galaxy, the Milky Way, there are over 100 billion stars. Multiply that by billions of galaxies, and the universe seems teeming with potential for life. And yet, we've heard nothing. No signals, no visits, no undeniable proof. The universe should be alive with civilizations, and yet, silence. This is the Fermi paradox, one of the greatest and most haunting mysteries in science. In this episode of Infinity Beyond, we ask, where is everybody? What is the Fermi paradox? Named after physicist Enrico Fermi, who famously asked, where is everybody? During a casual lunchtime discussion in 1950. He was referring to the contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for their existence. Given the age of the universe and the vast number of planets, advanced life should have arisen long before us and spread across the stars. So why haven't we seen them? Are we alone? Or is something preventing civilizations from reaching us or surviving long enough to do so? The numbers say they should be here. Let's break it down. The Drake equation estimates the number of active, communicative extraterrestrial civilizations in the Milky Way. When we plug in conservative values, we often get dozens, even hundreds of civilizations. And with space travel, even at modest speeds, a civilization could colonize the galaxy in a few million years. A blink on cosmic timescales. Yet Earth shows no signs of visitation. This silence is deafening. Possible explanations. Where are they? Scientists and thinkers have proposed dozens of theories to solve the Fermi paradox. Here are some of the most compelling. 1. We're early. Maybe intelligent life is rare and young, and we're among the first. The universe is still forming stars and planets. Life might take billions of years to evolve, and civilizations may be few, or just getting started. 2. They're too far away. Space is enormous. Even if civilizations exist, they may be spread thin across the stars. Signals may take thousands of years to arrive, and we've only been listening for a century. We might just be missing each other in time and space. 3. They're not using radio. Our searches rely on radio waves, but alien civilizations may use advanced technologies we don't understand. Quantum communication, neutrino beams, or something we can't detect. We may be looking on the wrong channels. 4. The zoo hypothesis. What if aliens are aware of us, but choose not to interfere? They could be observing us, like animals in a zoo, waiting for us to mature or reach a certain threshold of intelligence. We may be in cosmic quarantine, for our protection or theirs. 5. The Great Filter. One of the most chilling ideas. Perhaps there is a barrier, a filter, that prevents civilizations from surviving long enough to spread. This could happen at any stage. Life might be hard to start. Intelligence might be rare. Civilizations may destroy themselves through war, AI, or environmental collapse. If the Great Filter lies ahead of us, it means our future is grim. But if we've already passed it, we may be a rare lucky survivor. 6. Their undetectable advanced civilizations might become so efficient they no longer emit detectable energy. They could live in digital realms, on Dyson spheres, or in black holes, invisible to our current tools. We might be surrounded and not even know it. 7. They're already here. Some suggest aliens are among us, but hidden, visiting in secret, embedded in myths and folklore, or observing without contact. While these ideas drift into conspiracy, they highlight how uncertainty fuels speculation. 8. We're in a simulation. If reality is simulated, then the universe might be designed to appear empty. Civilizations beyond Earth might not be rendered unless necessary, or exist only in other simulations. A cosmic sandbox with only one player. What does silence mean? The silence of the stars could mean we're rare, we're doomed, or we're just not looking correctly. But it also means we must become the signal. If we are alone, we are the universe becoming conscious. We are the first voice in a silent cosmos. What comes next? Projects like SETI, Breakthrough Listen, and the James Webb Space Telescope are scanning deeper, broader, and faster than ever. New methods, like technosignature detection, are opening fresh avenues. Perhaps we'll hear a signal tomorrow, or perhaps we must be the signal, spreading life, knowledge, and meaning to the stars. Final thought. The Fermi paradox reminds us that space is vast and silence profound. But silence isn't proof of absence. It's a challenge to keep searching, dreaming, and pushing outward. Here on Infinity Beyond, we don't just ask if we're alone. We ask what kind of universe we want to create, if no one else is watching. Because if Earth holds the only voice in a silent galaxy, let it be loud, let it be wise, and let it echo beyond. If advanced alien civilizations exist, how would we recognize them? Would they look like us, communicate like us, or would they be so advanced that we couldn't even comprehend their technology? To answer that question, we need a way to classify intelligence on a cosmic scale. Enter the Kardashev scale, a framework for measuring a civilization's advancement based on how much energy it can harness. In this episode of Infinity Beyond, we explore the levels of cosmic power and where humanity might stand in the grand ladder of civilization. Who was Kardashev? The scale was proposed by Nikolai Kardashev, a Soviet astrophysicist, in 1964. He was studying signals from space and asked a big question. What kind of energy output would a truly advanced civilization produce? His answer led to a three-tiered system that has shaped how scientists imagine alien intelligence ever since. The Kardashev scale is elegant and ambitious because it's not based on culture, biology, or even technology, but on energy. Type 1. Planetary civilization. A Type 1 civilization can harness all the energy available on its home planet. That includes geothermal energy, wind, solar, and fossil fuels, ocean currents and tides, and atmospheric manipulation. This level of control would allow a species to master planetary systems, control weather, prevent disasters, and power a fully global civilization. Where is humanity? We're currently around Type 0.73 on the Kardashev scale, According to theoretical physicist Michio Kaku, we're still largely dependent on non-renewable energy, and we've only just begun tapping into our planet's full potential. But we're on the path, and accelerating. Type 2. Stellar civilization. A Type 2 civilization can harness the total energy output of its star. This might involve building massive solar collectors, creating Dyson spheres or swarms, megastructures that surround the star and capture its energy, using stellar fusion directly as an energy source. Such a civilization could power entire planets, terraform worlds, and colonize its star system with ease. To us, they might appear godlike, controlling the very fire of the sun. Some scientists have proposed that we could detect Type 2 civilizations by looking for infrared signatures of Dyson spheres, since waste heat would be inevitable. So far, no clear signs. But the search continues. Type 3. Galactic civilization. A Type 3 civilization harnesses the power of an entire galaxy. This level of advancement is truly mind-bending. They would use the energy of billions of stars, control over black holes, dark matter, or even hyperspace, travel across vast interstellar distances, possibly through wormholes or space-time engineering. Such beings may have transcended biology, living as artificial superintelligences or consciousness encoded into energy itself. To us, they'd be indistinguishable from gods, perhaps even shaping the evolution of other species across the cosmos. Could the galaxy already belong to one? Or could their existence be the very reason we don't detect them? Because they are so advanced, they choose to remain hidden? Extensions to the scale. The original scale had only 3 levels, but scientists have expanded it. Type 4. Universal civilizations. These would manipulate the energy of the entire universe, including dark energy or quantum fields. They might control space-time itself, create new universes, or rewrite the laws of physics. Type 5 and beyond. Multiversal civilizations. Civilizations that traverse or even create multiple universes, possibly living outside time or as pure information. At this point, intelligence becomes almost indistinguishable from creation itself. What about humanity? We are infants on this scale, but the Kardashev scale offers a direction, a roadmap to what's possible. It shows that technological growth isn't just about smartphones or faster cars. It's about mastering energy, expanding scope, and increasing agency over nature. Humanity faces many challenges: energy crises, environmental collapse, political instability. But if we can survive and evolve, we might someday reach Type 1 and beyond. Could aliens be on the scale? Absolutely. And this framework helps us search for them. If a Type 2 civilization exists, we might detect unusual heat signatures around stars, disrupted planetary orbits, artificial structures blocking starlight. If Type 3 beings exist, we might see galaxies dimming unnaturally, stars disappearing, harvested or moved, patterns in cosmic radiation. The Kardashev scale gives us a lens to look through, a way to interpret strange anomalies as possible intelligence. Dangers along the way. Each level of advancement comes with existential risks. Type 1. We must overcome war, climate change, and energy scarcity. Type 2. Harnessing stellar energy could be catastrophic if mismanaged. Type 3. Expansion across a galaxy may trigger conflicts with others, or with nature itself. The path to power requires wisdom, not just technology. The Kardashev scale isn't just about power, it's about responsibility, a new way to think about civilization. What defines advancement? Not luxury, not weapons, but energy and expansion. The Kardashev scale challenges us to think big, to view intelligence as a force that reshapes the universe. It's humbling and inspiring. It says, if we survive, we won't just grow, we'll transform. Final thought. The stars aren't just lights in the sky, they're potential fuel, destinations, and tools for civilizations far beyond us. The Kardashev scale is not science fiction. It's a scientific prediction of what's possible. And here on Infinity Beyond, we follow that possibility, one level at a time. So the next time you look at the stars, don't just wonder who's out there. Ask, what kind of civilization might be watching back? And where on the scale might we go? What if everything you see, this world, this room, even your body, isn't as solid or real as it seems? What if the entire universe is actually a hologram? No, not like the shimmering images from sci-fi films, but something far deeper and stranger. The holographic principle is a cutting-edge idea in theoretical physics. It suggests that everything in our universe, from galaxies to atoms, may be a projection from a more fundamental two-dimensional reality. In this episode of Infinity Beyond, we peel back the fabric of space to explore the question, is our 3D world just an illusion? What is a hologram? A hologram is a 2D surface that encodes information to appear 3D when viewed. Think of the image on a credit card or security sticker. It's flat, but when light hits it, you perceive depth. Now imagine that our entire universe is like that. What appears 3D, space, objects, time, might be information encoded on a distant, flat boundary of the cosmos. It's a radical idea, but it's grounded in real physics. The black hole connection. The roots of the holographic principle begin with black holes. In the 1970s, physicist Jacob Bekenstein discovered something strange. The amount of information, or entropy, inside a black hole doesn't scale with its volume, but with its surface area. This shocked physicists. Normally, you'd expect more volume to mean more information. Later, Stephen Hawking showed that black holes radiate energy, and this led to a paradox. Information seemed to be lost when a black hole evaporates, violating the rules of quantum mechanics. How could that be? To solve this, physicists like Gerard T. Hooft and Leonard Susskind proposed a bold idea. The information isn't inside the black hole, it's on the surface, just like a hologram. The holographic principle. This principle says that all the information contained in a volume of space can be represented as data on the boundary of that space. It's like compressing a 3D object into a 2D description. In 1997, physicist Juan Maldacena gave the idea mathematical strength through what's now called the ADS-CFT correspondence, showing that a gravity-based universe in a 3D space can be fully described by a quantum field theory without gravity in a 2D space. This was a breakthrough. It showed that reality might be emergent, built from a deeper, lower-dimensional reality we don't directly perceive. So, are we in a hologram? Not in the sci-fi sense of flickering images, but if the holographic principle holds across all space, not just black holes, then our entire universe might be encoded on a cosmic boundary we can't see. Our 3D experience of reality would then be like a projection, not fake, but not the most fundamental layer either. Some physicists compare it to a video game rendered in 3D, while the code and data exist in 2D. We're real, but the source of our reality may be elsewhere. Implications for physics. This idea could solve some of the biggest puzzles in science. Quantum gravity, unifying general relativity with quantum mechanics. Black hole information paradox, preserving information on surfaces. Dark energy and space-time. Geometry, rethinking what space actually is. If space, time, and gravity are emergent, not fundamental, then the real bedrock of reality might be information itself. In this model, bits of data, not particles, are the true atoms of the cosmos. Does this affect you? Philosophically, yes. If we live in a holographic universe, it challenges how we understand identity. Are we the projection or the projector? Perception. Is what we see a rendering of deeper truths? Consciousness. Could it too be emergent from quantum information? It also connects with ancient spiritual traditions. Hinduism's concept of Maya, illusion. Plato's allegory of the cave Buddhist teachings on impermanence and emptiness. Maybe science and mysticism have been touching the same mystery from different sides. Could we test it? In principle, yes. Some researchers are trying to detect quantum noise, the pixelation of space, as a sign of holographic structure. Experiments like the holometer at Fermilab aim to measure whether space itself has a grainy texture, as predicted by some holographic models. So far, results are inconclusive, but the effort is ongoing, because if proven, it would revolutionize everything we know about physics. A universe of information. What if the universe is a vast quantum computer, each particle a bit, each interaction a computation? This would mean that reality is information, and matter, energy, and space are just emergent phenomena. We wouldn't be any less real, but we'd be infinitely more mysterious. Final thought. The holographic principle doesn't say the universe is fake. It says it might be stranger than we thought. A deeper layer of reality where space and time dissolve into information patterns beyond imagination. Here on Infinity Beyond, we explore not just the stars, but the code behind the cosmos. Because to understand where we are, we must first understand what we are. Right now, somewhere out there, there may be another version of you, sitting in the same seat, watching this video, but with slightly different thoughts, or a completely different life. This isn't science fiction. It's the multiverse, one of the most thrilling and controversial ideas in modern physics. In this episode of Infinity Beyond, we open the door to infinite realities and ask, are we living in just one of countless universes? What is the multiverse? The term multiverse refers to the idea that our universe isn't the only one. Instead, it may be one of many, possibly an infinite number, each with its own laws of physics, histories, and realities. Just as Earth is one planet in a vast galaxy, our universe may be one bubble in a vast cosmic foam. Let's dive into the main theories behind this mind-bending concept. 1. Quantum multiverse, many worlds interpretation. In quantum mechanics, particles exist in superpositions. They can be in multiple states until observed. The many worlds interpretation, first proposed by physicist Hugh Everett, suggests that every quantum event splits the universe. Every choice, every possibility, every outcome, all happen in different branches of reality. In this view, there is a universe where you chose a different career, one where dinosaurs never went extinct, one where this video doesn't exist. Every moment spawns a cascade of parallel worlds, endlessly branching. It sounds impossible, but quantum physics leaves the door wide open. 2. Cosmic inflation and bubble universes. After the Big Bang, our universe experienced rapid inflation, a burst of exponential expansion. Some cosmologists, including Alan Guth and Andrei Linde, propose that inflation didn't stop everywhere. Instead, it continues in other regions, creating bubble universes, each expanding with its own space-time. These bubbles could have different physical constants, vary in dimensionality, contain wildly different types of matter, or none at all. We live in just one bubble, surrounded by others in a vast multiverse, and we'll likely never reach them because space is stretching too fast. 3. String theory and the landscape multiverse. In string theory, Particles are vibrating strings in a 10 or 11-dimensional space. The equations allow for an enormous number of solutions, perhaps 10 to the 500 different possible universes. Each solution represents a different way those dimensions can be compactified, resulting in universes with different particles, different forces, even different numbers of dimensions. This landscape of possibilities implies a vast multiverse, and our universe is just one valley among many. 4. Brain theory and parallel universes. According to some variants of string theory, our universe may be a 3D brain, short for membrane, floating in a higher dimensional space. Other brains could exist parallel to ours, just millimeters away, but inaccessible. Occasionally, these brains could collide, triggering events like the Big Bang. If this is true, entire universes could be stacked side by side, separated not by distance, but by dimensions. 5. Mathematical universe hypothesis. Proposed by physicist Max Tegmark, this radical idea suggests that every possible mathematical structure exists, and each one corresponds to a physical reality. If true, every internally consistent universe exists, regardless of how strange or incompatible it may be with ours. In such a framework, the multiverse is not just likely, it's inevitable. Can we ever prove it? That's the big challenge. Most multiverse theories are untestable, at least with current technology. Other universes would be outside our observable horizon, separated by inflating space or dimensions we can't access. But indirect evidence could emerge. Imprints in the cosmic microwave background from bubble collisions. Unexplained patterns in quantum data. Mathematical coherence of multiverse models with other successful theories. Science advances by exploring the boundaries of the unknown. The multiverse may be just beyond that edge. Philosophical and emotional impact. The multiverse isn't just physics. It's deeply personal. If infinite versions of you exist, what does identity mean? What is choice if all outcomes happen? What is the value of this moment, this life? Some find it liberating, a celebration of infinite potential. Others find it unnerving, a dilution of meaning. But either way, it expands our sense of reality far beyond imagination. Does the multiverse solve anything? Possibly. In cosmology, the fine-tuning of our universe is puzzling. Why are the physical constants just right for life? If there's only one universe, this seems improbable. But in a multiverse, we just happen to be in a universe where conditions permit life and observers. This is called the anthropic principle. It's not proof, but it's one way the multiverse might explain the unexplainable. Final thought. Whether the multiverse is real or not, the concept pushes us to think bigger than ever before. It asks us to abandon the idea that our universe is all there is, and to imagine a cosmos filled with endless possibility. Here on Infinity Beyond, we don't just seek answers, we seek perspective. Because the more we understand about the universe, or multiverse, the more we understand about ourselves. So if there are infinite versions of you, make sure this one lives with wonder. All journeys have an end, even the universe. For all its grandeur, galaxies, stars, planets, life, the cosmos itself is mortal. Born in a fiery burst 13.8 billion years ago, it has been expanding ever since. But what will happen at the end of time? In this final episode of Infinity Beyond, we confront the ultimate question: how will the universe die? The expanding universe, first, a reminder. Since the Big Bang, the universe has been expanding, not into empty space, but creating more space itself. Edwin Hubble discovered that galaxies are moving away from us, and the farther they are, the faster they recede. At first, scientists thought gravity might slow the expansion. Maybe the universe would collapse in a big crunch. But then, in 1998, a shocking discovery rewrote everything. Enter dark energy 2. Independent teams observed distant supernovae and found the expansion of the universe is not slowing down, it's speeding up. Some mysterious force, now called dark energy, is driving galaxies apart faster and faster. We don't know what dark energy is, but it makes up about 68% of the universe. Its presence reshapes our cosmic fate. Let's explore the leading theories for how the universe might end. 1. The Big Freeze. Heat death. This is the most widely accepted scenario. As the universe continues expanding, galaxies move farther apart. Over trillions of years, stars burn out. New stars stop forming, galaxies drift beyond visibility. Eventually, only black holes remain, but even they won't last forever. According to Stephen Hawking, black holes emit Hawking radiation and slowly evaporate. In the far future, perhaps tens or 100 years from now, even the last particles will decay. The universe becomes cold, dark, and silent. A vast heat death, where entropy reaches maximum and nothing more can happen. Not with a bang, but a whisper. 2. The Big Crunch. In this less likely scenario, gravity wins. Dark energy slows down, reverses or disappears, and expansion halts. The universe contracts. Galaxies race toward each other. Stars collide. Temperatures rise. Eventually, everything collapses into a single point, a cosmic implosion, the reverse of the Big Bang. Maybe it triggers a new Big Bang, a rebirth. But current evidence suggests expansion is not slowing, making this theory unlikely. Still, it reminds us of cyclical models, where universes may die and be born in endless loops. 3. The Big Rip. If dark energy isn't constant, but grows stronger, it could become catastrophic. In this scenario, first, galaxies are torn apart, then stars, planets, and molecules. Finally, space-time itself rips apart. Everything is destroyed, not by fire or ice, but by acceleration. This could happen in 20-30 billion years, depending on the properties of dark energy. It's speculative, but terrifying. The universe isn't just expanding, it's being shredded from within. 4. Vacuum decay, false vacuum collapse. This theory arises from quantum field physics. The universe may be in a false vacuum, a temporary, unstable energy state. If it decays to a lower energy state, it could trigger a quantum bubble of death, expanding at the speed of light, rewriting the laws of physics as it goes. Everything it touches is instantly obliterated. We wouldn't see it coming. It sounds like science fiction, but it's a legitimate possibility in modern particle physics. Reality, it turns out, may be sitting on a fragile shelf. Time beyond time. Some theories suggest the end isn't truly an end, but a transition. Maybe the universe becomes a simulation of itself, or collapses into information. Perhaps consciousness survives, migrating into quantum structures. Maybe advanced civilizations learn to engineer new universes, seeding them with life, intelligence, and meaning. Perhaps this universe is already someone else's creation. Could we escape? In the far, far future, could humans, or their descendants, survive the end? Some ideas include hopping between galaxies before they vanish, creating pocket universes, uploading consciousness into stable systems, engineering entropy-resistant civilizations. It sounds impossible, but if a species can last billions or trillions of years, nothing is off the table. Survival becomes a question of will, wisdom, and scale. Beauty in the ending. Whatever happens, one truth remains. We were here. We lived, loved, created, wondered. We looked up and tried to understand. Even if everything ends, the journey matters. Because meaning isn't just in the stars. It's in our questions, our art, our stories. The universe gave us life, and we gave it consciousness. Final thought. From the first atoms to the final galaxies, this cosmos has been a dance of energy, matter, time, and mystery. And here on Infinity Beyond, we've walked that journey together. The end of the universe may be billions of years away, but the desire to explore, to ask, to imagine, that's eternal. So no matter how the story ends, let's write our part with curiosity, with courage, with wonder, and with eyes always turned to the stars.